How are you doing this morning? No, I'm okay here. We're gonna start in 5 minutes, so we're fine. Yeah, how are you doing?
Catching up with
They took, so now you're going back, like the bad students are always in the last line, you're like, okay. Actually, I'm a little claustrophobic, so I always sit down very close to the doors, like, I just, so. That's good. So we're sure that we are connected to the online. Excuse me. May I have those screens on, please? Are those this? I turned it on, but it didn't work. I don't know. Oh, okay. Turn it on. Thank you so much. Perfect. Thank you so much. All right, good morning, everyone. We are connected also. Okay, I'm going to try to, no, not 30. Well, I hope everyone slept well and is well rested. We're going to have a full day today with a lot of material, so I'm going to try to go over, well, as much as I can. But anyway, all the slides are going to be available for you in case you want a little bit more of details. And again, as I said yesterday, I don't mind if you interrupt me for questions in the middle, right? Because that makes actually, that interaction is very good for everyone, because somebody can be asking the same questions as you do. So I don't mind to stop briefly and just explain and then continue. So if you feel or any questions right in the middle. Good morning to also all of the online attendees, and we're going to be the last kind of fundamental on water flow. Yesterday we saw the determination of the unsaturated hydraulic conductivity function, and I hope I think it is not a difficult thing to do. Now you know that there are estimations for that, if you can measure that or you don't have the time or the money, but also you can do stuff in the laboratory or in the field that can be, well, at least for the research side is important. Today we're going to see the water flow through unsaturated salt. I'm going to get a little bit more into the steady state and transient conditions. And I have for you a couple of examples that we run in Plaxis for you to know, to understand how all these theories apply to practice, right? So you're going to be learning about water flow, steady state and transient water flow. I briefly touched yesterday on that. And a couple of examples, one for an air dam, which is a classic sea pitch analysis, and the other one for flooding under pavement systems, that also you can just model on that, at least to figure out how these will impact your stiffness and how that will impact your design procedure. That's the important part, right? How you apply all this information to your practical engineering problems. So partial differential equations, I'm not going to go in detail. I'm not going to go step by step in here. I assume most of you have done that into your classes, math classes and graduate classes. But at least I'm going to show you what is the equations that we solve and we have solutions for and how to apply that. So like I explained yesterday, the CPH can be either steady state or transient, right? Both of them, the steady state, you're going to need the hydraulic head, we explained a lot on that one, and the coefficient of permeability or hydraulic conductivity, and they're kept constant during the whole process. For the unsteady state condition or transient conditions, we do the hydraulic head and the coefficient of permeability change with time. That's what is called transient, it's just time, right? And the hydraulic head changes with the boundary conditions with respect to time. What that means is that if you have any problem when you do have environmental conditions changing continuously, you're going to have always a transient flow condition in your problem, okay? So the examples are many. Infiltration through air dams is the classic example that you need to learn. Evaporation through unsaturated soils for those working on evaporation. Groundwater contaminant control also. Everything that moves, the water with time. And the water flow under pavement structures after a flooding condition, that a special case that I bring to this audience today. So how the hydraulic conductivity vary with the space, right? This is important because I find out that the main cause of inaccuracies when you model CPH analysis is the wrong value for these unsaturated hydraulic conductivities. We usually assume things, right? Assume things. So this is something that you really need to be careful when you are running any one of these analyses. For a steady state CPH through saturated soils, the case that you all know, the permeability is a constant with respect to time at each point in the soil. This is what we assume, okay? Why? Because we do have a condition, it's already saturated, right? So the fluid flow through the fluid flows through the fluid, right? And if it is 100% saturated, then you're going to have kind of the same permeability going on, okay? However, the coefficient of permeability for unsaturated soils change from one point to the next one, right? For all that Professor Bharat explained you today, 2 days ago, about all these different capillaries that you find full with water or not full with water, okay? Well, now the spatial variability usually in saturated soils, if we have any variability, is attributed to the heterogeneity of the soil, right? We got a little bit of heterogeneity, then we said, okay, that can vary a little bit. But for unsaturated soils, the permeability is not because of the heterogeneity mostly, is because of the changes in moisture content or matrix suction, okay? So again, 3 examples in here of how permeability can change in an unsaturated soils. I guess we can, I like to put it in groups so we can find the information easily when you need to get to it. So one soil, for example, you can have a soil that is heterogeneous but isotropic. That means, for example, that you do have in here, this one doesn't work in here. You got 2 points A and B. I hope you guys can see that well. For point A, the magnitude of the permeability is different from point B, right? So that's a high heterogeneous situation. The isotropy means that the permeability at that particular point on the horizontal and vertical direction is the same, right? So this is the isotropy condition. So you can have that condition, you can have heterogeneous but an isotropic condition, which you do have the permeability changes with respect to space, but at that particular point the horizontal and the vertical are different. But you can have the case that the two of them, the ratio between them is the same, right? It actually, it gets to the modeling is a little bit much faster if you assume that. Or you can have a continuous variation in the permeability with a space in which not only there are difference in the conditions of the soil because of spatial variability, but also the ratio between those two are going to be different. So spatial heterogeneity is the general case that we use for unsaturated soils, okay? And that's why the time consuming when we run those kind of problems, right? I mean, I'm talking about time consuming, probably will take you a couple of more hours, right? But for the design is much better, and the design, that structure that you're building is going to last 30 years, right? 40 years. So we need to be patient and being able to run all these problems. All right, so like I said, those are the three conditions I just explained. I just have it in here written for you so you can read your notes later on. Okay, so how we model that flow. If we just start with the typical one-dimensional flow that actually for us geotechnical engineers is the most common, because we're looking at very extended situations, and our problem basically is a vertical problem. The water flow under a steady state condition that can be generated either by infiltration or evaporation. Okay, so what I have in here is that usually when you have a steady state condition and you run a steady state condition problem for those, how many of you model all the time or do some modeling? I saw 1, 2, 3, 4, 5, 6, okay? So when you do that and you do, okay, I want a steady state condition, okay? You can just say basically at the top, we're not going to do any infiltration or evaporation. We're just going to figure out where the water table is, all right? And basically it's going to create a static equilibrium with the water table that is equal to gamma times the height, right? So it's a line that is a negative pore water pressure, right? We assume that the pore water pressure, the suction is, oops, here we go first. I guess this one is fine. We assume that the pore air, again, so just keeping that in mind, is equal to your suction, right? So I'm talking about that the line that we saw in there, okay, here we go. The line that you saw in here is the negative pore water pressure, right? So if you assume that the pore air pressure in here is atmospheric, you can assume that to be 0. That's basically your suction value, right, going up. Is your steady state equilibrium condition. Now, if that is the case, and if you have a negative pore water pressure at equilibrium with the groundwater table, this doesn't vary with time. Actually, that's the one that you have all the way when you run a steady state condition, right? So this one is, but what happens is, usually we do have all these influx or outflux, evaporation and infiltration at the top. And therefore, this line in here starts deviating. Whether you do have a steady state evaporation, your line is going to be twisted to this direction, all right? You're going to have more evaporation, so you're going to have higher negative pore water pressure. When you do have a steady state infiltration, you're going to have more water in here, and the line is going to twist on this direction, okay, until you get a steady state condition. If you run one of those steady state conditions when you have an infiltration which is kind of a constant, every day, right, or always is this one, you're going to have a steady state flow downward condition, and it's going to be running like that, okay? So this is important for us to understand, and this is what I wrote for this one. So now with this graph in mind, the three different water flow conditions can happen through the unsaturated soil. One is the static equilibrium, one is the steady state flow when it is downward, and a steady state flow when it's upward. Okay, so this is the pore water pressure, but also you have the gravitational head distribution, right? So you have those two heads in there, and this is the other head. This is the gravitational head that you do have due to the overburden pressure and to basically the height, right? That's the second head, and we just assume usually that the velocity head is nil. All right, so those two can be used to compute the hydraulic head profiles generated in the soil to different boundary conditions that you're going to have in the field. Okay, so these line to lines, as I said, can be explained, the water flow rate in the magnitude and the direction through the unsaturated soils. For that, we did continuum soil mechanics. And the continuity equation under the steady state condition, you're always going to have that for any element of soil, the mass of water flowing in has to be equal to the mass of water flowing out, right? This is your continuity equation that must apply always for our condition on this one. And basically, you do have the Q in minus Q out equal to 0. And the Q in minus Q out basically is your Darcy's law, right? It's just equation in which you do have the flow of the water for, I'm going to give you the Darcy's equation in a minute. This is just Q in minus Q out equals 0. And then because you can't just get this one out, and basically you can have a net flow through the element that can be written as this one, and this is just solving this simple math, and then you get the Darcy's law into that equation, right? And this is the flow rate, which is the permeability as a function of suction multiplied by the hydraulic head, and then you got the equation that yields that, right? This is the equation that can be used to estimate the hydraulic head profile for that. So we can write partial differential equations for that. In this case, well, because you do have one, and this one is also a function of that. So basically, we do have the change in water coefficient of permeability, K, in the y direction due to changes in suction. And this is the equation that can be written as a partial differential equation. And I'm not going to go through that, step by step. But I'm going to tell you the different conditions or the different cases that you're going to have. Let's say, for example, a saturated case. So this is the general equation, but you have an unsaturated or heterogeneous condition. For a saturated condition, that permeability becomes a constant, right? It's K sat. That's K sat right here, right? And basically, this one also becomes a constant, and this is your K sat. And we leave it like that because it's heterogeneous. For saturated and have homogeneous condition, we don't have a change in the permeability with respect to y or a function of the hydraulic head, and therefore that only applies to this cause, and this K, which is a constant, gets away from that. Okay, so that's the second case of the equation. Now this is just steady state condition. That's the steady state condition, the partial differential equation you're going to find. The second one is the transient CP condition, all right? When that happens, we now need to take into account not only the permeability function as a function of suction, but also we need to figure out what is the storage capacity of your soil, all right? Because you're going to be working that with time. And that's when the saltwater characteristic curve comes into play again. Many situations are encountered for that, where the ground surface is pretty much a moisture flux condition. You're going to have a transient flow. Everything that it changes in one of the boundary conditions, that is make the flow all the times to be continuously changing with time. So we got, for example, boundary conditions in here that are rainfall, for example, right? So you can put rainfall in one side, you can have no flow of water conditions on some other side, you can put water table in here or just a water table in between and no flow conditions, or you can put a total head, for example, okay? Like for example, if you put in here a water table, in here you can put that this one is your suction equals 0 line, right? Suction equals 0 means saturated. And then you can run the program with this one to be fixed, right? If you want the groundwater table to fluctuate, then you need to use another condition. All right, so you set up your program and you set up the first very carefully what the boundary conditions you need to work with, all right? Whether there is no flow here or a constant head condition, or if there is some influx or evaporation going on, okay? So those are the conditions that you're going to be allowed to do for every one on those models, right? And basically, the nice thing is about when you have the cover with the environment, these thermal boundary condition that you have in there can be an actual evaporation flux, right? And it's very interesting for us. So that means that, for example, you do have a actual potential evaporation for a particular site, right? And all these numbers we know based on the weather station conditions, okay? Now what we need to figure out is the actual evaporation that the soil is going to try to, get the water out. Guess what? Remember what the soil water characteristic curve means, the soil moisture retention, right? So that, the soil is going to hold some water. And even if you do have this actual evaporation, the potential evaporation, you're going to have only some actual evaporation going on, right? So this becomes a flux condition, very interesting for, I guess, a couple of you are working on evaporative things here. I didn't bring that example. So let's go for example, an air dam. And we're going to go a little bit more on the running fluxes on this one. But for example, during the filling process. So you make an air dam, you got, and I didn't put a coin here, just a simple air dam that has a filling process. It's going to be a transient flow, right? Because it's going to be varying with time, right? You're going to have to fill that reservoir on this side of the road. So you can go from here all the way to there, and basically it's a transient flow as the reservoir is filled. Once the reservoir is totally filled and you leave that level alone, you just don't change it, that becomes a steady state condition for the soil once it equilibrates. Okay, those are the two. So this is true if the water level is kept constant, and a small fluctuation can cause any infiltration of evaporation that it becomes transient in that point. Probably we don't do that all the time. We just do a steady state condition for the flow. But if we do have some situation, that the example I'm going to show, that we're going to be changing that reservoir level, okay? And that's important for that. All flows are heavily influenced by the conditions that you have in the unsaturated soil, and you need to consider the anisotropic permeabilities. Like I said, is important. Both directions that you characterize the material very well on that, is important. Is the first parameter that you need very well characterized, okay? And that's when you're going to tell your boss that I need money for this, right? Because we cannot sell short this kind of analysis. We need good data, otherwise you're going to get garbage, okay? No matter what models we're going to have. We need the questions that are derived based on these conditions, and the water flow properties are defined by the greatest and the least coefficients of permeability. Usually when you do have a very big project, you go ahead and check different places, right? You cannot run every single place. You cannot just change every single place. So we usually are conservative, and we do the maximum and the minimum that you can get, right? And then you work with those kind of values right there. Usually in here is a two-dimensional flow analysis. We neglect the Z direction, okay? Again, anisotropic means that the permeability depends on the position within the soil, okay? Matrix suction will vary with soil mass, and therefore the permeability will vary. We analyze the steady state condition by continuity of the water phase, and that the ported pressure is assumed to remain constant with time. Okay, ported pressure, usually you don't change it unless you're putting some suction in there that I don't know how you're going to get that. To model anisotropy, find the ratio between the largest and the least permeability values that usually give you a good value, or unless the one that is more predominant in your problem. Use the same ratio for any point within the soil profile, and you can do the heterogeneity, but you can simplify the program by just doing one ratio. For transient flow analysis, those are the partial differential equations you're going to need to deal with, or the program that you're going to be using or programming need to do. And this is the change in the permeability in one direction, and this is the change in permeability on the other direction. And this one is going to be the storage capacity right there. The M value, I'm going to show you in a minute what it is. And basically, this is the change in the hydraulic head with respect to space, and this is the change in hydraulic head with respect to time, right? That's your partial differential equation right there. And those values are function of the matrix suction, as you already know. And this value is what we call the water storage modulus, or water storage capacity. For isotropic conditions, you're going to have that this value and this relationship, because it's a function, and these ones are the same, right? It's isotropic. And therefore, you can use the same value right here and right here. And we still need the permeability function as a function of suction plus the saltwater characteristic curve. M value here, this is your saltwater characteristic curve. Usually, if you take the derivative of the slope of the curve, you're going to have the water storage of that, okay, for every one of the points. So which one do you take? Which one do you take? We usually take, for the problems, kind of a point right here in the middle for that, okay? We don't do the whole function analysis. You just take the water storage for that. But this is the value that you can take. Okay, so now this is all you need to run C-pitch analysis. You actually need those two hydraulic properties or function, the saltwater characteristic curve and the K and SAT function, okay, as a function of suction. Okay. Any questions so far? This very, very compacted material, right? It's not. Okay, everybody understood. Good. So a couple of examples in here that we run just to demonstrate how important this one might be in the practical application, right? And it's okay if we find that the difference are not much. I think when we run it is when we need to realize that if including all these parameters makes sense to you economically, it's okay. If you find out that it's not, fine, just run a saturated analysis with no problem, right? But I think it's important that you understand that some of the situations you may save some millions of dollars in here if you just basically do it right, okay, that way. Do it right means a little bit more realistic analysis. So what is the impact of water level changes on earth dam? This is a transient flow analysis, right? And usually when these water levels are pretty quick, and that happens when you have to, for example, to draw down a reservoir, okay? There is a danger, there is an earthquake happening, you don't want this water at this level, you want to lower that. There is a lot of a lot of rainfall, and this, is at capacity, so you want to lower that. There are many situations when you have the air dams have to be lowered down, okay? And usually you want to do it at a rate that is not dangerous for the excess pore water pressure to occur, right? So this is the typical case of a transient flow condition, right? And why it's important is because you can cause instability on this embankment or this side of this if you do it too quickly. So for that, we need to consider what is the pore water pressure monitoring inside. And sometimes we do have all these sensors in there, and we can figure out how much excess pore water pressure we got, and make the calculation of total stress minus pore water pressure, and figure out where your effective stress or excess pore water pressure is, and all of that. However, you will like some modeling as well on this one. For that, you're going to need a couple effects of the water level change and the stress field, and the water level change and the dam stability. So you have to have C-pitch plus instability, shear strength analysis, factor of safety, right? So you're going to need that. This situation requires unsaturated C. So it's good to know where the C-pitch and when the water is going. But you want to figure out also that this one is stable as that occurs, okay? So we run a little example in here when the level is defined. First of all, the long-term condition, a steady state condition, when the water level reservoir is at 25 meters, and two conditions when we need to do the drawdown. One, rapid drawdown, like you have to go from 25 to 5 meters pretty quickly, or a slow drawdown, and figure out how this will affect the factor of safety of your dam, right? This is right there in the practical application. So you did, we can do any assumptions in the program. The more you have run this before, then the more you're going to be understanding what kind of assumptions are going to be working or not. Usually I do it. I put the assumption and I don't put it. I run it. I figure out what the difference is. So you need to play with that because you need to take decisions, probably what assumptions you need to make for running those problems. Okay. So I neglect thermal sea pitch analysis, so I don't have that couple analysis. Interfaces, properties of the dam. Only consider dam, soil material parameters, and the groundwater table properties. Time-dependent effect of the hydraulic and transient flow condition. Isotropic condition, in this case we didn't vary the heterogeneity, but you know that we can put that in there, right? It's just to run a little bit faster. And assume the initial phase to be a steady state, and then by gravitational loading, and then we make a full couple flow deformation analysis for the transient drawdown, all right? So you create your geometry. For those of you, if you haven't done it, you will do it, okay? You're gonna do it either here or when you graduate and start working. See, this is the subsoil material, and we have that field. We got some core materials in here, which is usually the impermeable side, and basically you create this one is kind of an AutoCAD kind of similar stuff to do that. The dam height, put 30 meters right there, and the top and bottom widths 5 meters in here and 185 meters down here. Geometry, and when the parameters you need to start getting. So we use more Coulomb for the shear strength criteria. You can use any other parameters or constitutive models that you have available on the program has available. And we got for the coal, the properties for the core, for the field, for the subsoil. So what properties do you need? You need the unit weight, right? The gamma wet, gamma saturated below the groundwater table, gamma wet above the groundwater table. That's very important. And for the strength run, you're going to need the modulus, Poisson's ratio, cohesion and friction angle. These are the typical shear strength parameters you're going to need for that. And for the groundwater flow or the sea pitch analysis, we use the Van Genogten equation, to fit that one. And obviously, it uses Darcy's law or a modified Richards equation. Horizontal permeability, vertical permeability, the saturated value, we put them, this is the saturated, we pull them to be constant, right? Isotropic conditions. And then we tell the guy, just use the Van Genogten estimated equation that you saw yesterday to calculate the whole function, okay? And we give them a soil water characteristic curve data for all the soils in there, because you're going to need that. So, three analyses were run. The first one we call high flow constant case. Reservoir level was kept at constant level at 25. Then a quick drawdown when we watered the level down from 25 to 5 meters in 4 days. And the other one, a slow drawdown when we did that in 40 days, right? In 40 days. We got more time and we can do that. Assumptions, the water elevation drop was kind of a constant or linear as a function of time, okay? But you can do any assumptions that you believe is necessary. With that, we run the program, and then what you get is port pressure distribution, right? Port pressure distribution, whether they are positive or negative, right? If it's positive, is the one that you've been always using. The negative are your suction values, right? Your suction values. High port water pressure that were generated. You can see the high flow analysis in here. It doesn't look good to me. So what we got in the left corner, okay, near the left corner of the soil, when the flow water was kept constant, you can see higher port water pressure develop on this one. As you go down, right, on the slope, then you're going to have more port water pressure because you got water under the groundwater table, and then you get to a point when you do have all high port water pressures all the way down. So you increase with that. Now, when you do have a quick drawdown, we can see that the port water pressures were higher than the ones in here, okay? The port water pressures were high. But we found out that to be kind of the same. But wait, the problem is not the port water pressure, it's the excess port water pressure that you are putting together on that. And then we just figured out what the excess port water pressure were. And that's when you see the big difference. This is the one that's going to cause the problem for you. It's going to be the excess port water pressure, right? And you can see when you have a quick drawdown, the excess port water pressure in here are going to be much higher. That means the excess port water pressure means that the soil is going to have to drain out, right? To drain out at a certain rate. It's consolidation theory, right? At a certain rate to get to the port water pressure that you saw on the slide before, okay? And this one will have less port water pressure in here build up than the less port water pressure than the high quick drawdown right there. All right, so with this information available, we went and checked for the factor of safety. What happens with the factor of safety once you have these conditions, right? So we use a point on the top level corner of the dam, and we just run a slope stability analysis for that. You can use any methods. You know, there are many computer programs that have the method of slices, this Morgenstern, well, everything, you know, just one wedge, everything like, you know, you need to do for that particular soil, right? You can run that. And then we plot the factor of safety as a function of the deformation, and we can see here that the factor of safety is about 1.2 when you do have the steady state condition. When you have the slow drawdown, your factor of safety goes down. There are some excess port water pressure to about 1.6, and when you have the rapid drawdown, you got a factor of safety about 1.2. All right. So now with this information, you can make decisions how much time you're going to need to do the drawdown. Okay. So how much you want to risk. It all depends on the amount of time you have, the amount of money that represents, and therefore now you have some information in there to do a safe and a good engineering analysis for what you want to do, right? There is never a right or wrong answer. There are answers for you to take decisions. That's what it is. All right. This is example number 2. This is the impact of unsaturated flow under the flooring conditions on subgrade stiffness. And basically, this one also has a lot of assumptions in there, but I thought it was a very nice thing that, you know, what we can use probably to analyze. So here is the problem. The highways or the roads in the United States are managed by the State Department of Transportation. We got 50 states, we got 50 state departments of transportation. So we make, and this is a whole full lecture. I made a survey of what if they have an implementation plan in case there is a flooding event. And they all do have kind of an emergency response to that, right? But the problem is they don't know when to open the road again after a flooding condition. They just wait to the water to subside or run off. Then they go to big machinery over there to take all the debris out. And guess what? If there is not enough time for the water flow to get out of it, they're damaging the road with the big equipment they're putting there to get the debris out. Okay? So the flooding is not causing the big problem, it's their own equipment at the wrong time, right? Obviously, they want to open the road because, you know, there are thousands of people trying to get from point A to point B, right? And, you know, the infrastructure is, you know, so we need that. So we need to figure out what is the steepness, what is the soil conditions after a flooding, problem number one. Problem number 2 is to figure out how much time do you need to open this road. Very 2 practical applications and questions that you're going to need to sit down and help answering to the government. Okay, so the flooding, obviously, you got a lot of water in there, and then the water starts infiltrating the soil, if everything is paved and everything, they will find a way. The water will find a way into your soil, okay? Hopefully you're gonna have a good drainage. That's another point that we need to check, right? Have good drainage, but the water is gonna get, we do have over there, the roads are always have shoulders that have opened to the environment, okay? So we get the water from the sides. We got cracks on the pavement, so we got also water through cracks, okay? There are many ways to get water into this, into the subgrade of the materials, okay? And the worst thing is that will reduce the pavement stiffness, right? And the strength characteristics, although I'm gonna talk about stiffness because I think this is more fundamental to characterize the subgrade material on that, okay? Subgrade might get saturated, might not get saturated, we don't know, but the roads are unsafe. And not only that, you can damage if you put a big truck going on through that road if the soil has, the stiffness goes down tremendously. So our objective, this is just part of a project that we are finalizing and is getting very nice results. It was to develop a science-based or a mechanistic-based framework to assess what was the stiffness loss or the resilient modulus reduction, but also the recovery time after the flooding. To see how much time do you need to open the road. Now, if I can tell you that it takes 1 year to recover, 20% of the, it's your problem and it's your decision to know where to open the road, right? So with those two information, we can figure out with the time after the flooding when this Department of Transportation of agency can open the road, okay? So we make assumptions and, well, we create a big profile here because we got groundwater tables down there because we wanted to figure out for unsaturated soil conditions, right? So, but obviously we can put the groundwater table higher. We put it at 3 meters, at 6 meters. This is very, well, when I leave, the water table is 30 meters down, 30 or 40 meters. So this is pretty shallow actually. In here you're gonna have water tables. So we got an asphalt layer, we got a granular base material. Are you guys familiar with the AASHTO classification A1A? Okay, AASHTO classification A1A is pretty much a well-graded, well-graded gravel, something like that. There are some pavement engineers in here, better than, I have some in that. So I got an A1A soil for the base, and I get an A3 soil for the sub-base. An A3 soil is a poorly graded sandy material in there, which is very good for sub-base materials. And what I did is we buried the subgrade material. We put it as a very permeable soil, A1A, like a sandy gravel material, all the way to an A76 soil, which is a high clay material, right? So we vary the soil from gravel, sand, silt, and clay, all right? And we also vary the groundwater table, and we figured out boundary conditions. And the first thing we did was to, okay, before the flooding occur, you are expecting that the water below your covered area has tended towards an equilibrium condition, right? It's tending always. You always get infiltration, you get evaporation from the sides, from the environment that you have the roads, but there is always a tendency of that road to go through an equilibrium condition, right? Okay, so we assume that if we run a steady state condition, it will be a nice place to start, okay? We can start from any place that you feel is important, right? Like for example, if you know that there's been a whole week before that with a lot of rain, right? So you can probably run this one and have a profile of suction, not the steady state condition with the groundwater table, but lean towards any infiltration or evaporation, right? And you can start with this one. So we started from a steady state condition for the sake of showing that to you. We neglect thermal gradients, the boundary conditions, the groundwater table will remain constant, so we put a constant suction value of 0 right there. Lateral conditions, no flow, so anisotropic conditions just to run it faster, K vertical and K horizontal the same. Then we run the steady state groundwater flow condition, and then we got a transient analysis with the weather conditions. We put a lot of flood, and actually we simulated what happened in New Orleans, I don't know, 2004 or something like that. that it was the Katrina hurricane, and we knew how much infiltration, how much water went through that, and then we just start getting. I'm going to show you that in a minute. So again, we run the material properties. We have a 4-layer system in here, and we got the subgrade material properties for every one of the soils. For the granular beds, this is an example for the asphalt concrete. Again, these are embankments of the road, are also slopes. I'm sorry if I create a noise in here. 1 second. I can't see where to put this thing. Is that in this corner? No, okay. It's very tough. Okay, right here. Oh, okay. Thank you. All right, hope everybody can hear me now. I lost my microphone. All righty, so again, the slopes of this pavement on the sides, those are embankments. It's called road embankments, right? And every time you need to design for a road, and you're going to see that a lot in the afternoon, how we can just use the material stiffness that is needed for the design of the road, but also you need to design for the stability of those embankments. Okay, you have to put the right slope in there, and you have to run some slope stability to figure out what's going on in there, right? So we run also a couple analysis with the deformations analysis and the groundwater model. Why we did that? Because we wanted to see what happened with the flooding, but we didn't want to fail the slope before knowing what happened with the flooding through different soils, right? So in this case, we put a factor of safety equal to 1.5. And it said, no matter what happens, just keep the factor of safety of this road at 1.5, okay? So we organized those conditions, we designed for that, and then we were able to, so the maximum condition for water will not fail the embankments for slope stability, okay? Because I want to see the fluid flow happening there. But obviously, you can run those programs by telling them, okay, I want to figure out what is the slope stability of this thing, and see what it fails or not. So we ran more Coulomb for that. We ran the groundwater model for that using Van Genogten parameters again, Darcy's law, and these are the parameters for Van Genogten. Saturated, I should say saturated here, hydraulic conductivity for different materials and so forth. These are the saltwater characteristic curves we use. We just get some data points for A1A, A3 soil, for all of the soils. We run like 6 or 7 soils, and we just put the Van Genogten fit through that one to figure out the parameters. And based on this SWCC plus the saturated hydraulic conductivity, the program will use the estimated Van Genogten equation, so we don't do instantaneous profile testing, and they will create the two functions. So we got the SWCC and the K and SAT function for that. Okay, these are I just put in here the values that we use for that and the Van Genogten parameters. If you want to run a little bit of solver, okay, how to obtain A, N, and M with the Van Genogten equation. And these are the actual the square error that you get. This is usually you got the actual value, you got the predicted value, and you try to minimize the sum of the square errors for that, right? This is by what? By changing these parameters. Changing these parameters until you get that sum of the square errors minimized, right? And then you get the best fit to your data. I will argue to my student that this is not the best fit, but he will argue something. The data that we went through very low here, Van Genogten usually flattens down before. I told you that yesterday. So basically, it's very difficult to get Van Genogten to all the points on the high value, but it's okay for that. Okay. So these are the climatic conditions we impose. You can also impose any climatic conditions. We use 4 different places. Louisiana, when the rainfall and the climate is like your climate here, is very wet, humid, and the infiltration potential is much higher than the potential evaporation, all right? Florida, which is a little bit less, but still humid. Texas, which is kind of in the middle, start getting into the semi-humid, semi-arid regions. And then Arizona, when it's very arid, like with the evaporation, is much higher than the infiltration on a yearly basis. And for the first day, after we ran the steady state condition, we said, okay, now we run the transient condition. And we did is for the day number 1, we put some rainfall in here, which was the same. Again, we were kind of using the data that we use for the New Orleans flooding problem that we got. And there's a very, very large rainfall of inches per day, actually. It creates a condition of flooding. And then we ran for 3 months, for 100 days. And we just impose infiltration or evaporation. In this case, you can do a balance, right? You can do rainfall minus evaporation, and you can get kind of a infiltration balance, right, to that. And you can put runoff and everything in here. In this case, we said, okay, we're going to dump all this amount of water in a soil that is already at equilibrium with the environment. And basically what we're going to do is we're going to just impose some evaporation for 100 days. And you can put every day a different evaporation. You have weather station data, okay? Or you can put rainfall minus evaporation and get amount of infiltration or evaporation stage. So we impose an evaporation rate for every one of the sites that was basically found. That was actually this is the average annual evaporation rate for Louisiana, for Florida, for Texas, and for Arizona, right? So we got a lot of evaporation, like you can see in Arizona than Louisiana. And you're going to hear also about TMI. TMI is for Thorway Moisture Index. It's nothing but a measure of the balance between infiltration and evaporation, right? So this one will tell you the weather. Like I said, 20 plus 28 means it's a lot more rain. And now probably Louisiana is not that bad. Guwahati is about 50, 55. It's very high. -3 for Florida, -12 for Texas, and Arizona -52. And we took some data based on different dates. But again, you can organize your condition as you please. And this is the pore pressure suction distribution that we found after we ran this thing. Let's say, for example, what happened in a very gravelly soil, and this is for the subgrade material, right? So this one is your steady state condition. That's when you started, okay? And then for day 1, basically, you put all this water in there, and the suction goes immediately to 0, right? The water starts infiltrating until one point, and it goes like this. And then for day number 2, it starts recovering, right? It starts drying out again. So your suction is going to be greater, until it gets into a more steady condition with the new evaporation rate that I put as a new steady state condition. If I run this one probably forever, right? You know, you're going to get into the steady state condition that you got initially, right? Same thing happening here with a soil like an A6 soils, which is a silty clay material, and basically you start with a condition, but day number 1, when you dump all this water in there, the suction reduced, but not that much as the one on that one, right? Soil is less permeable, so the water is not going to infiltrate. So what we happen is that always we think that soil that are very fine grained material are going to be all the worst thing that we're going to have, right? Well, in this case, we're going to have more water in a sandy, gravelly material, obviously, right? So this is for day 1, and then it start infiltrating slowly, day 2, and then it start recovering as you go, right? So these are the suction. Notice something very interesting in here. If I had plotted water contents, and I got 3 layers in here, this is the granular base layer, this is the subbase layer, and that's the subgrade, right? If I had plotted moisture contents, probably you're going to have, let's say, low moisture, very low moisture contents, and then probably saturated for this one in here. But when you jump to the next layer, so you might have some water content in here, and then you jump to the next layer, you're going to have a moisture content in here, and you jump to the next layer, you're going to have a moisture content in here. It's not a continuity between moisture contents, right? Because you do have different materials. So they might be all saturated, and you're going to see the granular base is saturated at 15%, right? And the subgrade material might be saturated at 35%, right? So you do have same degree of saturation, but you do have different moisture contents. But what do you see here in the suction? Well, the interface between those 2 layers have to be at equilibrium. And the suction profiles should be a continuous function. Okay? That's why it's the fundamental parameter that you need to check. Because that's the reason, it's the only one that's going to give you that continuity on the functions that you get. Okay? So that's interesting for you to realize in this one, if you have. So this is the pore pressure suction distribution. It's in my GIAN did so how do I, what did I do? Okay. So I want to run a little, I had a little video here, so how do I run this thing? From here? It's nothing. I just show you with that. So I can do this in here. All right. Oh no, it is still on the writing thing. If you just click at the lower side, so how just have to come back and just get out of. Oh yeah, right there. I don't know if you can see that. Thank you. Okay. So if you see this one is the initial, that's the next one, the next one, the next one. You see what, I just, I wanted to show you how this varies with until you get to 100 years, to 100 days in that case. Anyway, so that's for you to see the lines a little bit because we got a lot of lines in there. So this is the pore pressure, the suction distribution. Thank you. And these are the results of the suction distribution on that. Again, if you have day 1, and let's say we are in Louisiana, which is very wet, and for day 1 you have one of the soils that are very permeable. Check on the granular material and the subbase material. The thing is, this is too big, but if I wish I can do that. If you get into I'm just trying to, doesn't work. Okay, I want to try to show you. And in here, if you see the interface between those two, I can touch this thing. All right, good. If you see the interface between those two, you're going to see that the suction values in there are much higher than the suction values in here. That means that the water infiltrated all the soil in here because it was granular material. But in here, it infiltrated and almost saturated the granular base material, the subbase material. But the soil below is more impermeable. So the water basically were hanging out on these drain materials or very high materials, which is pretty bad, right? So the water did not infiltrate all the way down. So the resilient modulus in here might be lower in much more at the beginning than in here. In here, nothing happened to the subgrade. But the granular-based material and the sub-based material got totally inundated, okay? And then after 100 days, if you start just dissipating all this water, then basically you see that the suction just increase to a point when everything dries again, right? This one dries less because the water, just to take water out also, it takes more time. Here. This is, we can do, that's what I was telling you about the degrees of saturation, right? For the granular-based material, you may have different degrees of saturation that for this, that's what I wanted to do. I don't know what I did, but that's what I wanted to do. Okay, and then in here, so now how I come back. All right, boom, boom, okay. So now we got suction values, all right? With the saltwater characteristic curve, we were able to get degrees of saturation, right? So we got all degrees of saturation. Now, how this is important to the practical engineering? So you did your work as a modeler, as a professional geotechnical engineering. You went to that point, and you go to the pavement engineering. Here are my results, right? These guys use this, or how do you guys, the pavement engineers in here, will use those results, right? So we do have a resilient modulus for the soil that is usually done in the laboratory at one water content condition. We do the resilient modulus at optimum, or we do the resilient modulus soaked, that we call soaked, which is the 100% saturated, and pretty much stop right there. You don't do more, okay? So you just do one value of the resilient modulus at one condition, and use this value, and use this value for the design procedure forever, okay, for the 30 or 40 years of your pavement. Well, this is the value here. That's your initial value, all right? Now, because we were able to run a transient analysis and being able to incorporate, I'm done with this. I'm almost done, so I'm not that bad. Okay. We are going to use that value of the change in degree of saturation with time and figure out, or the change in degree of saturation with respect to the initial one that we got, the optimum condition. Usually granular-based material are compacted at optimum condition, or plus or minus, so you got this value, okay? Or if not, you're gonna have to do some coring and figure out what is the density before the flooding to figure out what is your degree of saturation, something like that. But we do have a data before that, right? Which is this guy, the initial, and now you got, with the time, a change in degree of saturation. Well, we put together a model. This model is by Carlos Cari and me back in, 10 years ago, 12 years ago. And basically, we figured out for different soil types an environmental factor depending on the condition of your soil. When you have saturated condition, this is the optimum. Your degree saturation at optimum are usually about 75, 85%, okay? That's your condition. After that, everything is almost, get all the way to saturation. The material type doesn't matter. You do have a saturated condition. There is not a big saltwater retention difference between that. But when you get into the drier condition, and you get into soil that have a lot of clay, and WPI is nothing but the passing 200, the 75 micron passing value, multiplied by PI. That's how I relate the plasticity of the soil pretty much. Soil that are very high PI and WPI are clay materials. Some that are WPI equals 0, that is obviously non-plastic soils, right? So when you get into that, you can find that the factor of safety will increase about 2 times only for granular-based material, okay? When you have almost dry condition, let's say 75 minus 50, 25% degree of saturation. But when you get clays, you can get a factor, an environmental factor of 10 to 12 times. That means that your soil becomes like a rock. Have you seen a clay clot? You can break them with the fingers, right? And it's not because it has cohesion, because I don't believe in cohesion either, okay? It's because it has a lot of suction, okay? The water bridges holding those particles together, right? And you can break this suction with your fingers, all right? And that creates a factor of environmental factor that is much, much higher for those kind of materials. So you can do an environmental factor for every time step that you're using or you're looking at, and figure out what is the change in resilient modulus with time, okay? And this one is a great way for them to take, analysis and take recommendations for whatever they want to do. So for that, we needed the resilient modulus at optimum condition, the degree of saturation at optimum. We found them for different soil types. Oh, here is the correlation between A1A is JW or JP, or A76 is CHCl or kind of stuff. So you got that in there. And these are the reduction in resilient modulus, the maximum reduction right below, like 0.2 meters below the sub-base material. And you can see that for A1A soil, there's reduction about 10–15% maximum. But when you get into the A4, A6 soils, which are silty, clay, low plasticity, siltous clays, you get a lot of reduction. You get into the 65–70% reduction on resilient modulus, okay? And some of them will recover a little faster, right? It will recover faster in Arizona because you have more evaporation, right? Than in Louisiana when you have less evaporation rate, all right? So you can take decisions with this kind of data all the time. This one again, the resilient modulus, you can put the before and the after. This is the before value, and this one is going to be the after value. And this value they can use and figure out how much rotting they're going to have if they put this amount of traffic, how much permanent deformations or fatigue or all of that stuff, okay? And that's all I got for you. I hope you guys appreciate what, some CPH analysis, and it's not that difficult. It's just, to figure out a couple of properties, functions in there, and you can start running transient flow analysis. Have any questions? Sorry, I ran 7 minutes over your. Yes, sir?
Can you show the profile of such an isotone?
The suction profile?
Yes.
This one?
Yes. And ma'am, can I come?
Yes, come in.
Ma'am, the left one is the initial.
This one is the initial. The initial is the steady state condition. Is gamma water times height from the groundwater table. So you got 0 value, and as you increase, right? Remember that this guy in here. Okay, I'm going to show you the first thing, the first graph I show you. Okay, what is it? This one is this guy. Right there.
Negative for water pressure, no?
Negative pore water pressure, right? Saturated unsaturated condition. This is the groundwater table. I put it at 3 meters, and then you get all this. Like, the thing is, I did it on the other side, but it's the same, right? I did it with suction. So the negative pore water pressure is the same as suction. So that's your initial condition for that. And then you dump a lot of water. And what happened is, this guy dumping a lot of water, this thing is going to go like this.
From negative, suction comes to the positive. No.
No, this
The pore water pressure
the
is
pore water
negative.
pressure
Negative, and then
And
it
less
will
negative.
be Positive or less negative.
will be less negative. But in this suction will be positive to more positive, yeah. Yeah, so this one is in terms of pore water pressure, right?
Pore water
So
pressure,
that's
yes.
what I put in negative. But this one is in terms of suction, right? This one is in terms of suction.
Ma'am, pore water pressure, no? Pore water pressure is negative initially.
Oh, okay.
What
Well,
we-
I should have put suction in here. Sorry. Here we go.
Yes, ma'am. So this one will be the initial structure, initial condition, no? That left one. Because pore water pressure is negative.
Well, I said that it shouldn't say pore water pressure, it should say suction profile.
So suction is negative.
No, suction is positive and is high positive. This one is minus 130,
This one is
minus 130 pore water pressure.
Okay. If I consider.
So
that-
high
that-
suction is
Ma'am,
drier, right? This is
In
drier.
that case, if I consider that is the initial pore water pressure.
Exactly.
Okay.
No,
then
yeah, this is the
when-
initial suction value.
Then
This is the
when
initial
time
suction.
increases, when time increases.
When time equal
then-
1, it goes
yes,
down.
ma'am. Okay.
And it gets to 0 suction.
At zero suction, but okay.
So 0 suction means saturated condition, right? Total saturated.
But at the bottom, ma'am, why this curve is
Well, because here is the groundwater table.
so?
So the groundwater table has some capillary going on in there, right?
But
Still.
ma'am, but the time before that, the graph is on right side. But
Well,
if-
yeah, the time before that, this is your pore water pressure. Oh, that's, you mean that why is a little
Yes.
bit in here? Well, it's because the water table, you know, if the suction get, the water table probably went down a little bit or something. This one is 0, 0. You see that? So if you got a little bit in here, is that the model, we're not
Yes,
able
ma'am.
to get one
exactly
in here.
why it is on right
Don't
side.
get into little things, doesn't matter. It doesn't matter, but you're right. Okay, so in here there is a little bit of change in suction from 0 to 5 kilopascals. That means that it gets a little bit drier than it was before. So it means that the water table went kind of a little bit down, right? But this is all on the morally boundary condition that you have to accommodate probably to get the numbers, right? But this one is essentially 0 all the time,
Yes, ma'am.
like this one, yeah, exactly. You're right, thank you so much. Any other questions? Yeah, there are
Hello, ma'am.
modeling situation that you got, you're gonna consider that, you know, the model is gonna be doing something not to fail, right, not to crash. And this is probably one of them. Yes, Raul?
Yes. So, if we simulate this condition during the rainy season and we want to evaluate over 90 days, and what is the right time to quantify equilibrium moisture content along the season?
Well, if you have, this is your time, right? And what you're saying in here is, this is rainfall, right?
Yeah.
And probably some evaporation in here, right? So you do have some rain, a little bit of rain. And also you can have some evaporation in here because you are in a certain place when some evaporation occurs, okay? So what you're gonna have for every day is a balance between rainfall and evaporation, right? So which one do you consider to be an equilibrium value?
Yeah. No, at the end of the season, is it? No.
I believe that if you want to design for something, you're going to design for the worst condition. That might be, okay, I have a lot of rainfall in here, so I do have my resilient modulus going down. But you're right, you know, if you check that one, it said, okay, my resilient modulus start right here and get a lot of, so in here and then go down because of the rain, right? Start going down and, you know, some high in here and then going more down. So you're going to have this in here. Eventually, if you are designing a road for 30 years, ideally what you want to do is to figure out what is the average value that's going to happen. But if you want to include a little bit, this one is prone to flooding conditions, you're probably going to be adding a percentage in here or a percentage down in here and design for a value in here. But this one even might be even higher than the optimum or sub condition that you're always designing for. And you are saving that money in the, I'm telling you, 1 centimeter, 1 inch of asphalt is millions and millions of dollars.
Yeah.
Okay, and that's the only difference, your resilient modules.
And the software, does it allow us to place a wheel load at the top and see what is the deformation we get at the top of subgrade or something?
You're talking about software like MEPDG, like
Yeah. No, in this Plexus Studio.
in this one, yeah, you can.
We can.
You can put, well, still consider the overburden pressure because I put the densities of the asphalt, granular base material, and all of that, right? So I did that. So it will consider that. But if you put any more load, yeah, but it is considering the overload.
Okay.
Now, what is not considering is the resilient modulus changes due to the traffic load. There is no Hyversine load that you put in here. But supposedly, and you're going to see that, I'm just kidding. Okay, here we go. When you use this equation, actually the resilient modulus, that's going to be in the next lecture, right? I'm going to teach you how to get that value. And that is a function of your traffic load. So here is your traffic external load, and this one is your environmental load. You have the two loads. The problem is that, it's an uncoupled solution, but it's a solution that is easy to implement for practitioners. Okay? That are more complicated, that you're going to see that in a minute. All right, let's take some tea time, and let's come back in 20 minutes, right? Great questions in here. Thank you so much. All right, let's see if I can. questions online. There was one more. You have one more question. I'm sorry about that. Yeah.
Ma'am, I wanted to ask you regarding that piston depth versus suction plot where you're showing. Once the rainfall has occurred, and like as my colleague was asking something like why did the matrix section increase?
No,
at the depth
it
of
didn't
6
increase.
meters?
It did increase. It decreased.
Like there was a from the original day, we have found that like for a particular tree, it is actually increased slightly at a depth of 6 meters.
Okay. What is your colleague? All right. Hello. Okay. So the plot was something like this. Let's see if I can get that. You got it in there? Okay, this is not port pressure, it's suction.
Yes, ma'am.
Okay, so that's suction, right?
At this point, I
Right.
was just asking.
At this point, well, this is just probably some modeling problem.
Okay.
Don't worry
So
about it.
normally it won't occur.
Well, normally, if that occurs, it means that the groundwater table went down a little bit. So you got a little bit of suction. You see that it went down probably a few centimeters. Oh, that's what it represents, right? But it doesn't
we
mean.
can also say कि,
Yeah.
whatever original water pressure that is existing, it has gone more like it has decreased more
Yeah.
beyond the original point. That's why we are seeing some increase in
It could be that, and in here you see there is nothing happening in that. So this one did the model okay.
I'm raising this down because even I have seen the same phenomena in my modeling.
Yeah,
Like I'm actually modeling the embankment dam.
yeah.
I'm just studying.
And
the
this one is the last day.
Yes.
Okay, so if it's just finishing here, but when it's trying to keep going, so if we got more evaporation, actually, it's going to bring more water out. Okay, so this is, where is your colleague? Okay. It's out, the one that is, okay, so yes, you can,
This is port pressure, right? This diagram which you saw.
yeah, no, that's it's negative port water pressure.
negative.
So this one goes down, but the suction is hot air minus port water pressure, yeah. Yeah, all right. All right, a lot of questions. I hope I will have like 3 months in here. I need 3 months next time, Bharat. Yeah, but okay, so basically great questions in here, variation and people that has been doing that we did in here. Is on? Is sound okay? Did I turn it off? Is that okay? Higher. All right? Would that work? Just keep. All right. So we're gonna keep because we already are 8 minutes into this one and we got a lot of stuff to cover in here. I'm gonna try to go. So now you hear a little bit about resilient modulus this morning and why it's important. You haven't get to that yet, but it is very important. It's very important because you're going to see that we have tried, many different groups have tried to do characterization of the material based on different things, based on deviator stress, based on shear strength, based on confining pressure. But in reality, when you put in here a load that is dynamic or Haber-Sein, a load that is a repetitive load, we're going to have not only the effects of the soil just due to the load itself, but also to the shearing behavior of your soil, all right? So I'm going to just show you the material stiffness characterization that we are using right now or currently in the United States on the latest mechanistic design guides. Not the 93, which is still used very widely by many countries, but and also in the United States, but by the newest AASHTO pavement design guide. And then we're going to talk a little bit about drainage of low volume roads. Like you see, the water is the problem, and we're going to try to figure out something. So I always say that the road infrastructure is a backbone for the nation, right? And rehabilitation and maintenance are very costly, very costly. And yet, we have no choice. We have to maintain the roads no matter what, okay? We have to spend that money, and that's something that, despite this huge spending on road rehabilitation, the current practice in the United States and in the whole world relies on a very empirical models, okay? Empirical means that you may get something that is fundamental below that, but you get few points in here from your area, and you put a line in there, and you use it like it were the holy grail for the whole world, okay? Empirical models for the behavior of the subgrade materials are very widely used, okay? So if you go to the pavement engineering side, where we're trying to do all this geotechnical engineering, grade modeling, very like, you know, and you go to the pavement engineers and they don't pay attention to the subgrade. They don't pay attention. They put a low value there, and then they design for the worst case scenario, the worst case condition, right? These models are used in many parts of the world, and that's the problem, because once you put a model in here and you calibrate with these conditions, everybody else is using without calibrating for local conditions. That's a problem. So this is important that we characterize the material in a mechanistic way. What I mean by mechanistic way means that it should be a model that should be applicable for everything. Then you get your data and evaluate the model based on your own data, right? Soil properties. But the fundamental things should be the same for everyone, not just an empirical model, okay? So environmental conditions play a very important role in the material characterization of the material stiffness. All these external factors that we see here, we were talking this morning about precipitation and temperature a little bit, but also is a solar radiation, relative humidity actually, which is one of the main factors for suction, and the groundwater table depth, obviously, wind speed, all of them are external factors that affect the pavement and subgrade conditions, right? All these internal processes that happen in the pavement are a function of some of these environmental conditions, not just only the load that you're putting there, right? Not only the load. So moisture gradients, temperature gradients, freeze and thaw cycles, drainage, infiltration potential, all of them have to do with environmental conditions, okay? And all of them are being affected the material stiffness of the soil. It's important, okay? So why is important for pavement engineering that I do take care of the material's stiffness? We got put together a climatic model, and actually that climatic model not only take care of the moisture variation with the profile, but also the temperature variation. Temperature is important probably for us. It might not be important for some of the applications, but some of the applications when you do have freeze and thaw cycles and thermal cracking, the temperature becomes a very important mechanism. So if we do temperature distribution within the layers, depth of frost and thaw penetration, freeze and thaw cycles, change in moisture and suction, and the environmental effects that you saw this morning, adjustment to the factor of the resilient modulus, we all affect the main distresses for which we design a pavement system. I need you to understand that we do have very discrete analysis when we design for a bearing capacity for a foundation. We just have a number, right? Or slope stability, we got a factor of safety. Pavement analysis is different. Pavement analysis is a cumulative distress analysis, okay? So the way that pavement engineers, and I'm not one of them, do is basically they figure out what is the rotting or permanent deformation with time and figure out how this thing is going to change, and they put a limit. And they said, at this time, my road needs rehabilitation or fail, okay? And same thing for the rotting analysis, they do it for the thermal cracking, for the permanent, well, rotting, fatigue modulus, cracking and faulting for concrete pavements, and all of this. So it is a function of time. It's a function of time, okay? and you decide what characteristics you're going to call it failure or not. Well, we can do final element analysis, linear elastic analysis, and we have those permanent deformation modulus for unbound materials, and all of these are going to be a function of time, okay? And time are going to be a function of your climatic changing conditions, all right? So if you have in here the rotting going like that, the rotting is a function of resilient modulus, right? The resilient modulus is going like that. Resilient modulus is going like that, right? When you do have a lot of rain, your resilient modulus is going to go down. So that thing is going to go down a little bit and going to run parallel to this one, right? So, and when you get a resilient modulus increase, probably the rotting will, resilient modulus decrease, you got rotting increase, right? And you're running here. So all of these will add up with time for the decision that you're going to take, whether the time will fail at 18 years or 15 years, right? And all of this is money. So that's how it works. That's very simplistic approach, but this is how we do for pavement analysis and design. On top of that, we put on more, slope stability or road embankment stability and some other factors, but this is basically what we do for pavement analysis and design. Okay. So what we're going to learn today is the stiffness characterization, why it's important to be very clear on how to obtain that resilient modulus. And I'm going to show you some laboratory testing that we do for that, some field testing, and some empirical correlations if you have that proposal that you have to put together for, in 3 days, right? And you don't have the time to go to the laboratory to test that resilient modulus at optimum that I show you in the laboratory. So this is what we do. We test the laboratory, the resilient modulus at 1 moisture condition, maximum 2. You got resilient modulus at optimum or resilient modulus at a soak conditions, all right, at a soak conditions. And that way you use these values for designing, just everything. So we're going to show you these empirical correlations and some drainage considerations on that. So there are 3 means for determining the resilient modulus: laboratory measurements, field measurements, and empirical correlations right there. So we're going to go for laboratory testing right now, and basically what you want to do is to simulate a traffic loading, okay? And the test, we do it based on some measurements that Sid from California, Berkeley, I think, and his group of researchers in the 1960s postulated. That simulation is a repeated application of a deviator stress. Everybody knows deviator stress, sigma 1 minus sigma 3, right? That put on top on a confined specimen. So we're going to see that in a minute. Evaluating in a triaxial cell. Okay, so you had a large number of repetitions. I'm talking about 10,000 repetitions, right? Blah, 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 blah. Everyone takes it 1 second. You can just check. In 3 hours, you can get the test done. And basically, you change the conditions after certain number of repetitions. So I'm going to show you how. So this is the test. So you just basically impose, get a triaxial cell. You got a sample. I'm going to talk a little bit about that sample. And basically, you put LVDTs to measure vertical deformation and horizontal deformation. And that's why pavement engineering fill these cells with air, not with water. We do it with water, right? But they do pull all these LVDTs around for lateral, for horizontal deformation as well, right? And they don't, at that time, probably now there's some submergible LVDTs that are a little bit more expensive, but it's expensive, right? It's expensive to put those. So that's why they confine with air, because they put all these sensors right there. And they start doing loads, low repetition. And they do a lot of cycles, and basically the modulus is going to be your change in stress with respect to the recoverable strain that you get. In other words, you test it and you go up, and then you recover some. You go up and you recover some. And after 10,000 repetitions that the soil has equilibrated to that load, the last 5 repetitions you measure the recoverable strain or resilient strain. That's why it's called resilient modulus, okay? The recoverable strain, and you use it and you get the resilient modulus for that particular set of stress condition, okay? So once the strain is measured, the process is going to be repeated for a combination of confining stresses and for a combination of deviator stresses to reproduce the different stress states of the soil encountered in the field. The data is then making a regression analysis. You're going to have one confining stress, sigma 3, sigma deviator, sigma 1 minus sigma 3, and you got a resilient modulus. And you got, I'm going to show you, got probably 28 or 30 different combinations. And then you put in a regression, analysis, and you figure out what is your resilient modulus. Okay. There are two methods that are standard for doing laboratory testing. Have you seen that? Everybody taking payments in undergraduate? Okay, one or two. All right, so there are a couple of test procedures. One of the most common test procedures that is used in the United States and in the world is the AASHTO T307. I'm sorry, you may have your own, but I don't have that information. This is called the determination of the resilient modulus of soil and aggregate materials, and it's been used forever. And the latest one is the NCHRP. NCHRP is for the National Cooperative Highway Research Program, and is the 128 harmonized procedure. Okay, I'm going to talk about the 128A because I think this is important. I'm going to compare a little bit with the T307 in here, but I'm going to be talking about the 128A, but it's the same as the other one. Okay, so you got the triaxial cell. Like I said, you put your sample. I'm going to show you the dimensions in a minute. You put clamps in here to put your LVDTs. You put horizontal LVDTs, vertical LVDTs, and you confine it with air, usually at a particular confining pressure that you need, right? And you apply your deviator stress. The specimen preparation is if you have an aggregate base, for example, for coarse grain materials, an aggregate base, you use a sample which is 6 inches, 15 centimeters diameter by 12. So it's a big guy, right? It's a big guy. And if not, you use the subgrade sample which is 4 inches, about 10 centimeters, times 8 inches for that. All right. So those are the samples. So you have to have a couple of loading plates, right, at different sizes. This thing had to be manufactured for different samples in there. And you put the samples at any assemble of triaxial cells. And then you applied what we call a Haversine load, Haversine pulse load. All right. When you simulate earthquakes, what kind of load do you use? It's the sinusoidal, right? Load. For traffic load, we use a Haversine load, and it's also a pulse. It's a pulse. See if I can do this one in here. It's a 3 different load procedures depending on the material you got, and you got some time for this is time, and this is the load, and you have the seconds that you use, and you have one pulse that you use 1 second, and then you rest for 0.9 seconds, 0.1, and then rest for 0.9. And if you have the granular or subgrain material, you use 0.2 of a load, and then rest for 0.8 seconds, okay? Depending on the material that you have. This is how we use the Haversine load. And you do that one every second for 10,000 repetitions for one load condition. Okay, and then you repeat it for another 28 or 30 different. So the sequence of the loads. So how do you choose the sequence of the load? And that's very important. You need to minimize the probability of the test failure. Why? Because what you want to measure is the resilient modulus of the soil. You don't want to do permanent deformation, failure, kind of the shear strength, right? You want to load it to a point when you're not failing the sample, okay? Because you're going to have many repetitions on the same sample, right? So you don't want to fail it. So basically, if you just check any soil, right, any failure criteria for any soil, that's your failure line for this one. And if you use, for example, the classic approach that we had before, which was the T307, basically, you know, you got a confining pressure in here, and then, oh no, right here, and you start increasing the deviator stress, right? And you got stress paths that were this direction, all right? So what happened is, with the first confining pressure, probably after five deviator stresses, you're failing the sample, and you're done. And everybody's calling, why am I failing the sample? Well, because the stress sequence is not a right sequence, right? And you do that one for the next confining, and the idea was not to get close to this one, right? To finalize around here, but you never know what happened with the sample, okay? So this 128A sequence, basically what it does is uses a harmonized, a line of constant stress ratio, sigma 1 over sigma 3, which allows you to have this stress path, right? This stress path. And therefore, this stress path is a little bit more parallel to this. So you are varying in the next sequence, not only your confining pressure, but your deviator stress, right? And that way, you have more loads in here before getting into one that might fail your soil. So this is the sequence that we got, okay? And if you have, for example, a fine-grained material, the line of constant deviator stress will do something like that, right? All right. So there were, I thought I took this one out. Okay. I'm just afraid that I'm using the wrong, no, I hope not. It's too long, probably. There are different models. So you got all this data, right? You got 28, 30 different sequence, 30 different combination of loads. And you need to fit this information to a model, right? And there are, you know, since the 1960s, when Seed proposed this kind of sequence, there have been many researchers trying to find out the best model to represent the resilient modulus conditions, right? So you then use log models, semi-log, more complicated. They use two constant, you know, variables, two constants to fit the model, fitting parameters, models all the way to about 6 different constants. They use different predictors, stress state, like bulk stress. What is the bulk stress? In geotech, we don't use bulk stress. We use usually, you know, sigma 1, right? Maximum sigma 3, right? We use that. Well, bulk stress, we use the 3 dimensions, sigma 1 plus sigma 3 plus sigma 3 plus sigma 2 divided by 3, okay? And the tau octahedral is 1/3 of the, okay. I think, I hope I remember. Tau octahedral is equal to 1/3 of a square root of the second invariant, right? Sigma 1 minus sigma 2 squared plus sigma 1 minus sigma 3 squared plus sigma 2 minus sigma 3 squared, right? Something like that. So that's the second invariant. Those are so pavement engineering actually uses the 3-dimensional thing because they have point loads for these traffic loads. All right, so, and they use this one, or they use independent variable like confining pressure, cyclic stress. We've been using many, many different models. So which one is the right model? And that, you know, this is just few of them that I bring in here. Again, this one have all forms in which you include, obviously, the stress, and the response is the resilient modulus, and the K1, K2 are the fitting parameters that are a function of your material properties, right? So those are many, many models proposed in here. What I want you to see here, very carefully, to see if you catch the problem with these models. These models have K1, K2, great, you know, very stable, 2 parameters, but only they use the confining stresses. This one is pretty good for fine-grained materials, K1, K2 parameters. The less parameters, the best thing for you, but you have only the shearing stresses, tau octahedral, sigma 1 minus sigma 3, sigma, those are the shearing stresses, right? Doesn't include the confining pressure. Right. So now we get into the more universal models and more, and now we say, well, we need to include not only the confining stresses, but also the shearing stresses, right? So we got those two in here, and now they're a function of that, and now you have models that are called K1, K2, K3 models, because you got two more variables in there. And there are models that I said, well, this is a total stress analysis. I want something more effective stress analysis, right? In which I include my pore water pressure. So probably it's difficult to people measure pore water pressure on those tests, but at least I include a factor in here that, represents my pore water pressure, right? So there are models in there that are been trying to do. Some is log scale, semi-log scale, and so forth, okay? But this has been the sequence of putting together those models to represent the data from the lab. This is the currently used model in the AASHTO MEPDG. Like I said, the laboratory is now regressed to these values, and your job is to put them, make a solver linear regression analysis, nonlinear regression, and find K1, K2, and K3 for that particular soil, right? When you do have your confining stresses and your shearing stresses ready. So K1, K2 model, I just bring one. I have like 10 different examples, but this one is the SEED model, the SEED and IDRIS, 1963, when they use the bulk stress. This model doesn't account for shear stresses, as I said. This one is another one that is the deviator stress. This model approach is good for cohesive soils, but at greater depth they don't consider the confining pressure. K1, K2, K3 models. The more common one is the universal model proposed by Witzak and Jacob Busan, and it has both. The P sub A appears in all of these models because this one will make is normalized, right? Normalized, and it's easy to model when you have a value from 0 to 1 instead of having values all over the place. So all of them use the atmospheric pressure to normalize the stresses of the soil. All right, so this one is probably the most common model on the K1, K2, K3. This one made it to the design guide. And for example, if you use triaxial test condition, your sigma 2 and sigma 3 are going to be the same, right? So your bulk is sigma 1 plus, it's not divided by 3. It should be divided by 3. All right. And this one is the tau octahedral. When you use sigma 2 equal to sigma 3, you default to this equation. This one, why? Okay, I need to check. Okay, so I'm not going to talk a little bit about, but what happens with those models is I don't see in any place that include the suction, all right? And suction is a fundamental stress state variable for the soil, right? The soil changes moisture content all the time. Suction changes all the time. Why we don't use suction on these models, all right? So they fail to do that, right? So these are models that, and I bring in here something that to me I think is important that you understand how important it is. Like for example, I'm talking about Harris sitting here again, 1967, when he shows the change in resilient modulus based on R value with water content. Look at the big change in water content. It's huge. It's huge change. And like, different, compaction conditions also is going to be changing, right? If you have this one on the wet, dry side of the wet side, but this is big changes. And there is a paper on the effect of moisture and freeze-thaw cycles and deviator stress on material stiffness from Willie Zhu in 2021. And he considered the important factors, and he considered a lot of tests and a lot of materials. And he found out that the density is very important for that. Then the soil properties, the WPI that I showed this morning, the passing 200 times PI. Then the water content. Look at the water content with the number of repetitions in the traffic. It's more important. He found it to be more important. And more important than the deviator stress by itself or the confining pressure by itself. This is very important. If somebody is telling me that he's been checking analysis and the water content on the soil for a payment analysis and decide is greater than the traffic load analysis, that's something. So It's very important, you need to consider that. So there are to be some suction-based models available from that. And there are many suction-based models. This one for the, the ones from the schools of Freeland in here have recognized this graph. And basically, if you have your groundwater table in here, I talk about my stress state variables that are fundamental. For a saturated soil, it's going to be my total stress and more pore water pressure, right? This is your effective stress. For the unsaturated soils, we can talk about the total stress, the pore pressure, and the pore water pressure, right? And then you can combine them in a way that you can measure them. You can use the three of them separately, or you can combine them, and that's what we did. We combined them in the net normal stress in here, which is the total stress minus the pore pressure, usually pore pressure 0 atmospheric, right? So that's your total stress, basically. And this one is your matrix suction that you've been looking at and very familiar now with that. Pore minus pore water pressure. So those are the stress fundamental variables for the unsaturated soil mechanics, or the negative on above the the unsaturated soils. So based on that, a lot of this is the models that you've seen include, most of them are total stress analysis when you have only sigma 1, sigma 2, and sigma 3 total. When you get into the saturated soils, then you don't have any suction, right? The only thing you have are your effective stress, sigma 1 minus sigma water, which is your sigma 1 prime, right? Sigma 2 prime and sigma 3 prime, right? The effective stress for that. When you jump into the unsaturated soils, then you're going to have not only your net normal stress, but also you're going to have your suction applied to the three phases, all right? So this one is the stress state that we deal with in any unsaturated soil. And for triaxial conditions, again, this is okay. For triaxial conditions, sigma 2 equals to sigma 3, and then you just get into your total stress analysis. You have your equations in terms of total stress. For the saturated, you got in terms of effective stress, which is 3 times your pore water pressure, right? Because you have sigma 1, sigma 2, and sigma 3. That's the tau octahedral for that, which is the same shear stresses. Whether you have water or not, you're going to have the same stresses, right? And the unsaturated condition, then you're going to have your net stress, which are your total minus 3 pore air pressure, your tau octahedral, which is the same no matter what the water is, and you're going to have your suction value. So those are the stress conditions that we deal with when you have unsaturated soil, all right? So methods that incorporate the suction, I found many methods, but I think I divided into 3 different categories. One of them are those that use the effective stress from unsaturated soils, okay, which I don't like it at all, okay. I'm the school of I don't like effective stress for unsaturated. I hope I convince you that the suction is independent, right? It's independent of your external loading applied. Is the environmental load. So Bishop proposed a model for that was very empirical in nature and was very popular. This is the first model that people start using, but it's inaccurate for the degrees of saturation less than 85. So you can use them probably good for saturation more than 85, but it's attractive for implementation processes. This is the model by Bishop, and it's very close to an effective stress, right? You have your net normal stress in here, like your total stress, plus your suction value multiplied by the famous Bishop chi parameter, okay? And that chi parameter is a function of degree of saturation. So now we got a material that should be independent, also a function of suction, which you have the suction here, so it doesn't make sense, okay? Because you have now a soil property that is a function of the stress that is represented, all right? So it should be independent. So I don't like, but Bishop is good because what happened is, like let's say for example you are teaching, for those who are in the academia now, and you are teaching bearing capacity for something, and you have a soil profile in here, you have your groundwater table, and you ask the students, okay, draw a pore water pressure profile in here, right? And what they're going to do is, or what you guys are, undergraduates going to do, you're going to do this one and 0 here, right? That's your pore water pressure profile. Bishop analysis, because of that, it's going to allow you that the pore water pressure is going to have a certain value in there, right? So with this thing, pore water pressure, you can create a confining pressure and effective stress pressure, like, before it was effective stress, probably, I don't know, something like that, and then just jump, lower because of the pore water pressure, but now you're going to have a little bit more because you have the suction value right there. So it's easy to implement, it's easy to show them that the effective stress will increase a little bit because of that chi parameter and suction parameter. Second model, second way of doing is a factor that considers matrix suction independent of the contribution of the applied pressure, and that's what we saw this morning. Resilient modulus at optimum condition plus an environmental effect, right? That's going to be your tutorial in here to figure out that. And it's mechanistic in nature because it includes now the two stresses that are, the externally applied loads and the environmental loads. It's a decoupled approach, and I put in red what I think it is, not that good, but it's relatively easy to use and easy to implement. That's the one that is being used in the Ashton design guide in the United States. We use the WITSAC model. These are the total and the octahedral external loads, and the environmental factor, as you saw, will represent the factor that, related to the environmental conditions, right? The third model is more fundamental and said, well, why we don't include the suction in the laboratory testing, right? Why not? Well, we can put a triaxial cell and actually measure pore pressure and pore water pressure. And we can do that, all right? Or we can put the sample at a moisture content, and then you have your salt water characteristic curve and you know what your suction is, right? So why we don't do that? Well, the apparatus is a little bit expensive if you want to put pore and pore water pressure, right? The triaxial cell, I don't know, sells right now for $150,000, right? But nonetheless, you still have a way to do a surrogate, like with water content, and figure out what the suction value is as you do. And we got a lot of work on this one. And we came out with this, actually, Palanivellu is one of my dear Indian students, right, from India. And basically, he worked a lot in the lab on this machine, and he come out with the Z1, C2, C3, C4, K1, K2, K3, K4 models, right? He put Z values in there, but actually he put the net stress, the tau octahedral, and he included the suction in here. That's a fundamental model, okay? Now what you need is going to be on the regression analysis to find the 4 parameters. You're going to need a suction column, right? But now I hope for you it's not that difficult to get that suction column in there, all right? So this one is rigorous and mechanistic, all right? Obviously it requires laboratory testing for calibration because you need K1, K2, K3, K4, right? But requires final element modeling because, you're going to need that value changing with the time and difficult to implement. So how we do that? Well, again, we use a triaxial testing machine. We had a high air entry value here. We measure the pore air pressure also here, and actually we build up on the top cap, and we put a pore air pressure and the pore water pressure transducers in here, and we measure that, and we actually modify. We put the same harmonized protocol to do that, and just put it in there, and we just were able to get very nice values. Okay, this one is, for example, what happened with, we used that model for undrained material with the universal model that is been using R² of 0.70. This one gets to 0.95. So you see that now the contribution of the suction in the model is now being reflected by improving the model a lot, right? So this is important that you understand and consider being important. And this one is even better. This one is for the drain material, an R² of 0.25 with the best model we are using right now in the whole world. All right? With this kind of models that we got at a square of 0.88, because suction is very important. All right. How to get K1, K2, K3 if you don't have a laboratory testing equipment like that, all right? Probably some of my practitioners here will be very interested to hear that, right? And there are some data that was used. I think Rahul was talking about the LTPP, the long-term payment performance test. This data is available for everyone to download. It's a big data from the payment engineering groups in the United States, and it has so many sessions all over the country. The nice thing about this one is they do have resilient modulus measurements in the laboratory. So you can get the data, and this is what von Quintos did, and in 1998, and some other people did, they have regressing coefficients for selected constitutive equations. They use the universal model mostly, and for different soil physical parameters. So they got all this database, resilient modulus, K1, K2, K3 from the laboratory. They got soil parameters, PI, Atterberg limits, passing 200, density, water contents. And basically what they did is they used that, this is the universal model, and they put together values, empirical values for K1, K2, K3 for that thing. Based on what? Passing 3/8, passing 4% of clay, liquid limit, optimal moisture content, and so forth. This one is for coarse grain materials. So they use compaction characteristics. For silty and fine grain material, they use percent clay, PI, water content. And they use K2, fine grain soils, they use more parameters. So they do have now, of course, this is now empirical, right? You need to be careful because you're going to be using soils that were not used for the calibration, all right? So you need to be a little bit more careful on that. But there are, like this, I can show you 10 different papers on different calibrations for that. So there are ways to use the K1, K2, K3 models for that. Okay, so this is what I got for laboratory tests. I hope you understand how we get the famous resilient modulus in here, right? And how we can modify those results to include suction values, which I think is important. Field testing, I'm going to go quickly on that. We use the application of deflections. Everybody, anybody of you have done falling weight deflectometer in here? Few, 2, 3, okay. This is the test we do. We use what we call a falling weight deflectometer. A falling weight deflectometer. And basically, what we do is we use that one. It's a non-destructive test, and it has a plate, a loading plate. And basically, this is the little card, and you got the plating here down. And depending on, there is a size for this one. I think it's 15, 20 centimeters, or 30 centimeters for that one. The lightweight is less than that. And you have the load, and you apply the load, okay, to this one. And then you just go and apply loads on that one. Every time you apply the load, you're going to have a deflection basin. Okay, so here is this a dropping weight of the pavement surface from a predetermined height onto a loading plate with a diameter of, 30 centimeters, right? 30 centimeters in here. And the magnitude of the load, this is important because this is how you estimate the sigma, right? The load that you're putting in that can be varying by changing the mass and the height of the drops, okay? Based on that, you also install velocity transducers in that beam, and you mount them in a bar, and they measure the deflections that occur when you put the load in here, okay? So obviously, the farther you get from that point that you apply the load, you're going to have less deflections, right? Less deflections. And this is what we call a basin. You find out a basin, deflection basin for that, okay? And if you can see, you can get that deflection basin into a model, right? Or into a function, okay? So once those deflection measurements are measured, you know the layers. You have to go to the field. You need to figure out what is the density of every layer, and you need to figure out what is the height of every layer, okay? And basically what the program does is that back calculate what the resilient modulus might be by exactly matching what you observe in the field, the deflection that you observe in the field, with the deflection that you get to, with the resilient modulus that you get to get exactly that deflection basin. Okay, so that's what we call a back calculation. Okay, back calculation layer moduli of the payment. And again, there is a whole lecture in here, or all the questions we use for that I'm not bringing in here. We also have portable falling weight deflectometers that are smaller in size, and they have different, obviously they're a standard size for that, but they're also very affordable to get. Okay. So what are you getting after that? Usually the influence depth is approximately 1 to 1.5 times. So if you have less than that, you're going to have composite deflection. I'm not going to get into those details. But back calculation in a nutshell, if each layer is considered to be an elastic layer, that's mistake number one, right? If you have clays, they're not elastic, they're elastoplastic, right? But you consider elastic layer in theory. You consider that each layer is isotropic, has the same properties, and homogeneous, and all boundary conditions are correct. So you do have a lot of assumptions. But it is possible to iterate various combinations of modular until you get whatever it is. And obviously, it all depends on what values you start with. Those who model, you're going to see that the initial input parameters are very important, right? Because when you're getting more than 3 layers, it's going to be very difficult for you to do it. So you do several iterations until you find a perfect match between the theoretical and the measured falling weight deflectometer measurements. Usually you use sigma 1 and sigma 3, that's your deviator, so you're going to need the coefficient of lateral air pressure at rest. I'm going to get into that. Need density and the thickness, and then you can put all of these, and there are back calculated programs that are actually available, most of them online and free. All right? Modulos, MATCAMP, ILBAC, WestDev, Julia. I mean, there are many of them are available. And you actually put whatever you get, and you just get your resilient modulus for the field. This is obviously, field testing is much faster to obtain many data points, right? But also you have to deal with the variability of the system, and you need to have experience on getting these, basins very well measured, everything. So I will say that this is more like an art than a science. But nevertheless, this is what we use all over the time, falling weight deflectometer to measure resilient modulus in the field. This is very good because it's non-destructive, right? So there is advantages for that. The time and the cost is much less than the laboratory testing, obviously. And basically, and it's because you can do a lot of more tests in a little amount of time. Non-destructive, means no disturbance or sampling on that one, so you got a lot of more money for the buck. So this is great. And obviously disadvantage, you cannot control the changes in the densities of the moisture contents on the field, and obviously the approach is linear elastic. The theory is linear elastic, and basically it doesn't apply for all the soils. So this is the second thing that you use to get the resilient modulus, at least the most, you can get it from other things. You don't have laboratory testing, you don't have field testing, but you need some data, okay? So we jump into the empirical correlations. Again, these are to be used with care, and you need to make sure that, those are preliminary analysis of a stuff like that. Okay, estimation of resilient modulus is obviously of interest when you don't have time. When you're doing a proposal to get, you have to put something, in a week, or that you need some numbers rather quickly to the design, or basically, you don't have the money, or it's a small project. And there are typical correlations, and probably you recognize some of these in here. CBR, California bearing ratio, is the most famous and actually used all over the world, okay, including the United States. Half of the United States or more than that use CBR instead of the resilient modulus, right? Our values, the structure layer coefficient, they use grain size and Atterberg limits, soil properties for that. Even they use classification to just get a number for that, okay? So CBR values, this one is probably the most important, and the one that you're going to be, and actually again, this is what the design practicing engineers do all the time. They use CBR. They go and didn't bring the test of the CBR, the California bearing ratio, that you do is a test that you put some material in a mold, okay, and you test the deflection or the deformation at different loading categories. It's a measure of strength. It's not a measure of resilience. It's not something dynamic. It's a static test. So that's why I don't like it, okay? It's a static test, all right? Nevertheless, there are some information in here for the Shell Oil Company is the one brought in 1960, very used. It's a linear equation. So you got the CBR value multiplied by 1500, voila, you got a resilient modulus right there, right? Equation derived from wave propagation tests, and you got at least you got the original data, at least you know what is the variability associated with that. This one is the U.S. Army Corps of Engineering, using in 1975. It has now a power equation, 54 times 100 CBR 0.71. Here is the data. You use data from Shell, from AASHTO, road test in Texas, and so forth. This one is the TRRL, the Transportation Road Research Laboratory, and this one perhaps is the best equation I've seen. Okay, 2555 CBR to the 0.64, and that was the adopted actually on the AASHTO Wear Design Guide. Okay, when you put in the guide, I have a CBR value instead of a resilient modulus. That's the equation that the program will use for that. There are limitations. I do believe, I want to bring that out, and I always found my payment engineering when I go to this one. CBR is an easy thing, and it's like the Terzaghis, saturated condition, right? It's been there forever, so everybody thinks it's the best thing to do. It's not. Okay, it's not. It's widely used, so there is a lot of data, but it's a measure of shear strength. Again, I mean, we're talking about resilience, and I talked to you about the importance of not failing the soil, right? And now they're failing the soil to get that value for resiliency. So I don't understand that, right? It's not correct. Besides, CBR is based on, do not recognize the stress dependency on modulus, okay, as you increase the loads, and therefore I critique this to be inadequate. But a lot of people have to bring it in here, because that's the first you're going to be looking at when you get into the practice. Layer coefficient, AI value, this is how you get the layer coefficient, is a function of the heights of this one. That's actually how you do that for the back calculation modulus. Okay, these are the equations that you use. Poisson's ratio, modulus, the height of every one of the layers, they're related with the structural layer coefficient, all right? This is, again, how we calculate these layers. This one is the equation that they use. You're going to have those equations available for you to use if you need that. This is the nice thing about this, and I got the reference as well. They are valued when the place where I live, we used R values. It's from the Asphalt Institute, 1982. The R value is also another test that you do in the laboratory. I didn't bring that in here, but this one is the adopted equation also for the AASHTO design guide. Correlation with soil index properties, very good for us because it's easy to get passing 200 MPI, right? And DCP, dynamic compenetrometer, because we use a lot of data in the field for that. So there are equations for that as well. This one is correlation, the CBR with the soil index properties. and then you use the CVR resilient modulus to get, resilient modulus. This one is actually the best we were able to do for the coarse grain materials. This is in the design guide. And this one is for fine grain materials also, a function of WPI. Empirical correlation, when you include also index properties plus the stress. You mix them and you do a big regression analysis. It's easy to do regression analysis. You include in here water content, both and deviator stress are there. So they got water content, deviator, and shear stresses, but it's empirical, right? This one is a little bit more fundamental. Has a deviator stress in here, has two parameters. It's like K1, K2 parameters, right? Those are the questions that you get for that. Hyperbolic models, and it's more a constitutive relationship actually. Fine grain soils also, they have equations for that, so I brought them all for your notes right there, right? Problem with these equations that are empirical in nature, they're a function of the data that is used to calibrate them, okay? You need to treat them at least with some of the data that you got. And the resilient modulus, again, is a mechanistic parameter and depend on a soil index properties and also the stress state of the soil. Okay. So that's what I got for resilient moduli. I hope you got a very good idea of how to measure that laboratory field, or some empirical conditions, that empirical correlations you still can use for that. Okay. Drainage considerations. I think this is very important because the whole thing about this is about the water, right? If you can control the water, then you can control probably many of these changes in the stress state, and therefore changes in resilient modulus that are undesirable. So from the, I'm sorry, I didn't bring I got the reference at the end, but I didn't bring the reference in here. Sarin-Ghetto. He said 3 of the most important aspects of road design are drainage, drainage, and drainage. Okay. If you take the water out, if you control the water out, then you're going to be controlling many of these things, right? So clearly showed that the bearing capacity of any unbound granular material are affected by changes in moisture content. I hope we convince you on that in the last 3 days. For coarse grain material, because you have a more drainal conditions, is the effect is less significant. The change in resilient modulus is less, actually. But when you have dense graded, remember when you saw the granular material, I was talking about an environmental factor of 2. But when you have a dense graded material, then you do have more changes, more considerable changes. Why we use drainage in the subgrade? Well, we want to lower the groundwater table level, close to this one. You want the water away from your babies or your infrastructure, to intercept lateral load, okay, of the subsurface water beneath the pavement structure, and to remove the water that infiltrates on the pavement surface. Okay, the biggest problem is when we have a slope, a road section, and the biggest problem is when we have sloping hills, right? And Professor Bharat showed you here many examples on the first lecture, right, on how this affecting not only regionally but all the world. Protecting ditches is probably very important, and I think this is the best thing. Although we were, discussing last night, I think over dinner, that it's almost impossible to maintain all the ditches, right, in a town, in a place. So it's difficult, but stop falling of material into the deep, aid the clearance, everything, all this ditch should be clear of any debris. And this is the first thing you need to teach. Almost time. I'm going to give you 5 more minutes in here. And so basically you need to get that ditch clean all the time, all right? Clean of vegetation, and this one will actually help a lot. Roads must have a ditch, okay? If the ditch is missing, pavement will be damaged. I'm talking about low volume roads, any roads that you do have, a lot of water to get a weight on that one. And I'm going to show you that the problem is, the lack of this, you get the water in here, and you start getting deformation because you get water accumulated, all right? Not only that, you get the water into places that you don't want them to go. Let's say a soil that, changes volume, like we're going to see next, or soil that are compressible and, you don't want water in there. Or simply, you're putting the water on top of the pavement with creating the potholes and all the stuff that you don't want to happen. So surface drainage control is important. You can do it in different ways, like a crown section, like, trying to do that. Out of a slope, so basically get the slope in such a way that you get the water out. For this kind of, designs, you're going to need to make sure that you put in the water in a safe place. Because sometimes you do that one without taking care of this side. And basically you are creating something down the slope, okay? Or in a slope with a ditch, right? You get in a slope with a ditch. Also rolling grades are important. You got all these low volume roads, right? And this is an unpaved road. And basically what they do is they do a rolling pass that is lowering than the road. Obviously not good for high speed roads, no more than 20 to 50 kilometers per hour. But this one make this one, and then also they do on a slope going down, and they cover that slope with some material that do not get the fines out of it. And this one seems to be working pretty well, and is much cheaper than a culvert, right? Culvert is basically the best thing to do to protect this one, but to put culverts every once in a road below, maintaining that this one that doesn't get anything is complicated. Okay, practice to avoid. What you want this is the water out of there as soon as you can. Okay, so you need to design ways of getting the water there as quickly as it gets rain. Okay. Long sustained road grades that concentrate flows are not good. Discharging water onto erosive soils, unprotected soils, not good. High boiling grading. You see a lot of people that send the technician to the field or the inspector and said, okay, I want you to figure out that the grades are okay. And instead of, taking a proper slope grading, inclinometers level or survey, equipment, they just go and they say, oh, that's okay, okay? They just look at it and say, oh, that's okay. Sometimes it's not okay. So you need to do a good job with the grading. Okay. Modeling drainage benefit. Modeling is very difficult. Drainage is very difficult to put it in the model, okay? Because you don't know what's going to happen. You can do any model and say, okay, this soil will not get more saturation than this amount, right? And you can model something like that. But it's very difficult because you don't know where the water is going in the field, okay? But we can estimate some benefit of putting a good drainage in there. And Bernstein and actually and Serenketo got values like, for example, the number of repetitions in here, as a function of the strain. If they use that equation, they use one for a soil that is undrained over the soil that is drained, okay? They can figure out that, this equation shows that basically the strain that you get in here are going to be a function of, that's going to give you the benefit of having like the ratio, going to having the benefit of having the drainage system. So maintaining and improving the drainage system is perhaps the most cost-effective measurement on roads where inadequate drainage is the main cause of deterioration. So you got roads in there that got a problem with drainage. That's what you need to pay attention to, okay? Then if you need to get the water in and you now know how to model the water and trying to figure out what's going to happen with that, fine. But the first thing you need to know is to avoid the water in the first place. Right? All right, you guys have any questions? Very general. I wish I got more time, but I hope I give you with good questions for lunch. Yes.
There is one question.
Yes.
Hi, Prof. This was
Hello.
a great lecture. So I would like to ask, as you mentioned about environmental loading conditions, including the pavement soil mechanics. So how we can consider the effect of Philistine cycle for calculating the resilient modulus? Means, through these equations, we have not considered any effect which is going to affect the increasing the water, if means increasing the ice or something in that. Can you explain about that?
Right, thanks for your question. So the question is, you've been talking about moisture variability in the soil, but what about frost, frost and thawing, which is also very important on the behavior of the, the stiffness of the material. This is a great question, and you're going to be here in the tutorial this afternoon. So you better be here
Thanks.
because I'm going to be answering your question right there, okay? Yes, we should be including, didn't bring obviously how we include it, but I can explain you what we do for that. But yes, we do include not only the environmental factor, but at the time you put the environmental factor, okay, that environmental factor actually can change depending on the condition that you have in the field. What you're learning here today was the environmental factor for unfrozen material. But once you get the switch between the temperature to be, above zero or below zero, you immediately switch the environmental factor from unfrozen conditions to freezing conditions. And what's going to happen is, and I want to just talk to me very, very quickly, when the soil freezes, the effect that it has on the resilient module is actually shooting it up very high. Actually, the soil gets very stiff. And the freezing is not the problem for the resilient modulus, because if the soil remains frozen all the time, the resilient modulus is going to jump from 30,000 psi to 100,000 psi, 500,000 psi. The problem is, after the freezing, what it comes is the thawing. And when the thawing occurs, these are all the problems that occur, because that resilient modulus not only goes down to the equilibrium condition, but goes even lower than that, goes to half of it, all right? Half of the resilient modulus we have, because now we got extra water in the system. So how do you accommodate that extra water? If the soil can heave, it was heaving during the frozen. Now you got less density material, less dense material, and you got what the pavement people talk about, the supersaturated situations, all right? And now your resilient modulus goes down, and then it starts recovering with time, right? All of this, what we do in the design guide, we put them very empirical, right? We put a number of the resilient modulus that shoots up and then goes down all the way down, that depending on the soil type, and then the recovering time is also considered that depending on the soil type, all right? But all of this can obviously be modeled on this one, but this one we consider the resilient modulus on this period of time to vary that way. And then when it becomes unfrozen, then you go with the right condition that you learned this morning. Great question. I didn't bring this one in here, but you're going to see a little bit of how to estimate the depth of frost penetration and the free swelling, mechanism in the afternoon. All right, guys, I think we went through too long, so okay, we're not that bad. 10 more minutes. All right, so I'll see you in Convey after lunch here, 2:30, right? So I'll see you then at 2:30, and thank you very much. Any questions from here? All right, I know I'm going to have somebody having questions later. All right, I'll see you then at 2:30. I don't know if I. Oh, okay. So if I do this one, I get. I'm playing here now. All right. class is dismissed. Well, I hope everybody can hear me. Right, 2:30. Let's start right now. So we finish almost on time. I hope you guys had a little bit of rest and a nice lunch. Great. I've been happy eating Indian food. Oh. The bread is spectacular. Alrighty. Yeah?
But here is canteen not much spicy and
Yeah, I said please don't spice it. Yeah, please don't give me too much. But I'm eating curry, which is a lot of curry, which I love it. So yeah, I don't eat much spicy, but yeah, I've been enjoying it. All right, so we're gonna have a couple of hours in here to do, first of all, talk a little bit about sensitivity soils to environmental conditions, right? What are the soils that probably are soils that you're gonna encounter also in your practical engineering life that you need to know a little bit about that. And probably you've heard about that on your soil behavior classes and or the volume change classes that you may have had on your graduate semester. So this is going to be the first hour. The second hour is going to be related to the environmental factors that had actually a lot of questions about that, and so pretty much I prepared a set of slides to guide you over to do a little exercise that I hope you complete before Friday, right? And then I consider you graduated if you do that. But it's pretty much to estimate the environmental factor and all the models that we use and all the steps we use to do that. So I'm going to talk about probably 15, 20 minutes on that and then let you guys know and do, and we need to divide this group into this, okay, some people will use this condition and this condition. So we'll do that on the second hour, a little bit more dynamic and for you to work and for me to stop talking. All right. So soils, sensitive soil. Sorry. Got a little bit of spicy to it. I like it. Not that much, yes. All right, so what you're going to learn today, well, there are some subgrade conditions that require especially sign attention, and this is, I'm going to bring in here 3 types of soils for you to consider or to, I'm going to talk a little bit of collapsible soils because they're also common. And these are totally different animals from expansive soils. Expansive, when you have expansive soils, you also have a shrinking or contraction. Has nothing to do with the collapsibility that you find on these soils, are totally different. And the frost susceptible soils that also you may encounter working in other regions in here. So we're going to go for a little bit of the mechanisms of ground freezing and how in pavement engineering they consider that to predict the frost depth and the frost heave prediction for some of them. All right. So collapsible soils are, very much encountered in areas. All of these soils are encountered. You got more problems when you do have arid or semi-arid regions. Obviously, if you have an area when it's wet all the time, you're not going to have too much variations of the water content. And remember that the change in volume for these soils is not a function of the change in stress, right? You're leaving the stress alone. The stress that you're changing are the environmental loads, all right? The environmental loads. So if you have a change in moisture content from low to high or high to low, then you got the volume change on this one, which is totally different from the consolidation theory that you all learned, right? Which the change in volume was a function of the change in effective stress, right? Or the dissipation of excess pore water pressure. So collapsible soils are usually found in arid and semi-arid regions, and this is when they do more damage. And basically, it happens because the water evaporates from the soil a lot, and leave all these little salts in there. Okay, little salts in there that will just, create like a kind of honeycomb structure, all right? And it's very strong. If you're trying to load these guys dry, they show a very nice shear strength, okay? The problem with that is when you wet them, okay? If you, for any reason, the irrigation failed and you got a lot of water out of sprinklers or something happened to that soil and you had a broken pipe or something, and now you get a lot of water in there. The soil actually will weaken immediately. That honeycomb structure will weaken and will totally collapse. Professor Bharat showed you there are collapse can be 1-2 meters. I've been called from friends at the south part of Arizona when they have a big yard and they put water irrigation, something damaged, and the next day you find out a big hole in your backyard, right? All of this goes down, and so that's how it is. So where they're finding, they're found in here when those soils, like for example in here, this is Arizona, that's where I live, and we got some soils in here on the south, and there are some other soils in here. Loess is the main deposit. Remember what loess mean? Is the wind, right? The oleic deposit, right? So when you have wind, and this is one of the ones that creates this, these conditions as well. Here in India, you also have some, and they appear when you have the desertic and arid regions, the northeast of northwestern of India. How they occur, like I said, aeolian soils or loess are one of the main ones, but also soil that are transported by water, which we call alluvial, soil that we transport by gravity, which are the colluvial soils, and soils that form in place by weathering rock that we call residual soils. So there are from all of the origin. And also we can make actually collapsible soils. If you make a collapsible soil, when you compact the soil, the optimum condition to compact will be close to the optimum condition and to the maximum that will give you the maximum dry density, right? What happens if you trying to compact a soil dry or optimum? Well, you create a soil that has much lower density, right? And you do have all these, conditions that are very prone to collapse if you let this condition dry and then wet, okay? So man-made soils out of compacted feed of low density, the dry optimum moisture content will be very flocculated, and you will actually make a collapsible soil right there, make a product, right? They also can extend, that's the problem, few feet down to 200 feet down, okay? It's very bad. So when you have few feet, okay, let's wet all this thing, right? 2 or 3 feet, let's wet it, let's collapse it before we build our structures. But you have 200 feet, it's gonna be tough to do that, all right? So you can see sediments of 2 to 3 feet are very common on that. Very big holes, these are caused by collapsibility. Also in roads is important. And obviously it affects the structures that are light. And the structure number one that is light is the pavements, or just residential construction or 1 or 2 story buildings. How do you recognize those guys? They have very low porosity, very high porosity, very low unit weights, okay? So you're talking about 70 to 90 pounds per cubic foot, or 12 to 14 kilonewtons per cubic meter. To characterize this is important, like you see the origin of the soil that you see here. If you see that there's a lot of loess in here, please suspect about collapsible soils. And there are also ways to do that, right? Indirect correlations or direct measurements of collapsibility. So we're gonna go through some of them, but you can do it in non-disturbed way, like, well, these are not disturbed way. Actually, you can do that on a disturbed way. Those are all indirect correlation. We're gonna check some of these. So this is the laboratory test. We actually have a laboratory test for collapsible soils. It's the D5333, and a standard test method for measurement of collapse potential of soils, collapse potential. All of these samples that you collect, those are the ring samples, the typical 1 inch by 2.5 inches, of diameter. Basically, you have to have them undisturbed because the structure is the important part of it. So you just don't remold it. Don't remold it. You need to go ahead and trying to do very, little disturbance and undisturbed sample that. And you perform what we call one-dimensional response to wearing test. Okay, you can do a one odometer test or double, and it's exactly the same odometer test that you do for consolidation analysis. When you have your sampling here, and you put it in a little box. Yes, sir?
The mic is not working.
It's not working.
Something.
Right here.
Hello, hello. Hello. Hello.
Hello.
Okay, now we can hear.
Hello.
Hello.
Yes, we can hear you.
Okay, great, thank you. Okay, now I'm gonna try to put this one back. Now can you hear me? All right. All right, so we do have the typical odometer test. And basically, we put the sample and we load it at the overburden pressure that you want to check, right? If you calculate your overburden, does it work? No? It's okay? All right. So the overburden pressure that you want to do. So basically, you load this one, and you're going to have a dry curve, a little bit of, sediment in there or collapse. And then when you have it at the overburden pressure you want, and that thing has stabilized, then you inundate the sample, right? You wet it. And immediately what you're going to get is a collapse, totally collapse of the soil to a point. Okay, this is the wetting collapse soil. And then if you keep on even increasing the overburden pressure, it will just go kind of a line parallel to the initial value that you have, right? Okay. I think it's the pen. So this line pretty much is parallel to this one, right? So you can do this one in two different tests. Like usually you can see that you can do one test in here, or you can probably collapse the soil and keep working in here, and you should get pretty much to the same point. So that's the way that you do a collapse test. It's very simple. It's very simple. Obviously, the most important part is that your sample is very undisturbed. Okay, so because any break in the sample will just cause a difference in the results. There are site characterization as well. We've done it, and actually it's better because you have a larger volume to test, and it's good if you can do that one. It's a fun test. We've done it in the field several times. Minimize the disturbance because you are just testing the soil in situ. And at least the difficult to sample materials can be characterized. And the disadvantage is basically it's a little bit more complex process in that. And there's a couple of them that I can just check. One is what we call in situ collapse test. And basically, what we do is we do a trench in the soil around it, and then we just put, settle down a small asphalt concrete pad, and excuse me, on that we put just boxes that we get in any, in any store, warehouse, store, or something like that, and we just fill it up with soil or whatever the overburden pressure that you want to load, right? Okay, so. Without that, and we use soil crates actually, or boxes on a concrete pad. And once you put this one in here, well, you do have some dial gauges that are, attached to a reference that is away from the site, and you just put a beam in there that you can put something around, and then basically once it's ready, you go ahead and inundate the site, right? You just put water around. We had a U-Haul a little bit full of water, and I remember I was inside that U-Haul, and my colleague disconnected from the truck, and I went out with water and everything to that place. That wasn't funny, but we got some accidents in the field. So once you do that, when you inundate everything, and basically you measure how much is that. Now, the problem with that is the following. In order to do settlement calculations, it's like any other settlement. You measure, this is depth, and you measure the strain, that is the deformations over the initial value that you got. And once you have a strains around this one, you need to know where to stop, right? To figure out what is the summation of the strain over the depth is going to give you your settlement, right? It's the same thing that you do for collapsibility. But the problem is, where do we stop, okay? So you need to figure out what is the degree of wearing that we get in the field to do that. All right, so which is a little bit difficult to obtain. There are also ways to do it in a borehole. We can drill a hole in here, and we put a small plate in here, and we load it, and we just fill it out with water, and then we can do some collapse tests like that, and just figure out how much it will collapse. Again, then you have to excavate and figure out what was the extent of the wearing that you did, in order to figure out what is the depth that you have wearing. There are many sources of water. This is what you need to avoid when you have these soils. Mostly are due to urbanization. Landscape irrigation is a big problem for that. Okay, soils that have never been touched before, and then now all this urban development goes to these places. Okay, and now you have a beautiful house with nice irrigation around. Guess what? You find a lot of holes around your house the next day, right? So broken water or sewer lines, stuff like that, poor drainage, big problem. Pavement of surface as well, and capillary rise. All of these might cause some collapsibility on your soil. How can we increase infiltration? Sometimes we feel, okay, well, it's not that bad. It's been raining here always, and we don't see that collapse. Like, for example, in San Diego, California, an annual precipitation is 30 centimeters about. Well, irrigation of golf courses can increase the water to 120 and 70 centimeters equivalent rainfall. Okay, so imagine the amount of water that we put on these soils, and basically we collapse the soils, right? Irrigation, golf course development, field regions, all of this results in collapse of native alluvium and deep engineering fields. This one, for example, it was a septic tank put in there for a family of 4 in 1 month, one of those farm areas. And I think in a matter of 1 week, that was injecting about 17,000 gallons of water into the soil at a depth of 10 feet down. And basically, the collapsibility was 2.2 feet. I mean, you could see the soil just going down. Okay. There is a lot of subsidence problem because of that. If you have deeper deposits of collapsible soils, okay, and you get water in there, then you start, making collapsibility as well. How do you do the settlement computations? Well, again, you need to estimate the surface flux boundary conditions that you have. How much water you're going to be putting in there is fine, but the thing is, we usually inundate it, so we just consider this to be saturated condition, right? You need to find the depth of equilibrium. Again, there is some area, and this is very difficult for us to figure out. There is a depth in which the environmental conditions, whatever we got for rainfall and evaporation, will be affecting the area. And all of this vary depending on the area that you're going to be located. All right. So that depth to equilibrium suction, suction may vary. Remember that if we had hydrostatic suction, will be something like that, right? Hydrostatic suction will be something like that. Now, you're going to get a point in which this infiltration and evaporation will allow this to do this or that, right? In this case, all the suction will be the same for practical purposes, right? So this point is your depth of equilibrium suction, right? Depth at which the equilibrium gets together. Well, there are places in the United States, when, for example, when I lived, it's been calculated that that depth is about 11 feet, 3 meters, about. But if you go to San Antonio, it can go all the way down to 30, 40 feet down. So that means that eventually the environmental condition might affect a much larger deposits on these areas than in other areas, all right? So I'm going to show you a way to calculate the depth of wetting. Hopefully I have it here. So this one is important, again, because we're going to make a summation or an integration over the area for that. You perform the response to wetting test in the lab. You get the collapsible strain, right? And then you perform the calculation. That's what I was showing you right now in a minute. And this is the depth to equilibrium, so I'm glad I included it. This is a work that done by Jeff Van and Sandy Houston in 2021, in which they went and checked several areas on semi-arid regions of the Southwest United States: Arizona, Texas, New Mexico, Utah, all of these areas. And they also collected data from the literature all the way back to from McKean collection on 1981, and they figured out, you know, where the soil suction will come to an equilibrium. All right. They find out, and I'm going to show you how they did that in a minute. It's interesting, and it's very easy. The depth at which the climate-driven fluctuations in the soil began to stabilize and equilibrate, and they were able to relate the depth with the Torwent Moisture Index that I was talking to you. Okay, the TMI is one area that I'm going to be checking on the next hour. Okay, it's basically a way to measure the it's kind of a balance between the precipitation and evaporation. All right, and they did a very nice. I think they found a very nice relationship. You can see that areas like Guwahati, minus 50, 55, the depth to equilibrium suction is very high. It's about 4 meters down. All right. So you will expect a lot of problems because the environmental conditions might affect, you know, deeper areas. But if you are in,
Sorry, actually depends on the groundwater table. Or groundwater table is very shallow.
oh yes, okay. This one is when the groundwater table is deep.
Yeah.
This one is groundwater table is deep. You know, thank you for the acceleration. If the groundwater table is shallow, then they stop, right? Because you got now the suction. Exactly. So if you have deeper groundwater tables, you know, you're going to have a suction at equilibrium condition at any point. But if you have groundwater table in here, this is going to be your suction equal to 0, right? And then, you know, that from then that's going to be helping. So if you do have a groundwater table all the way down to what, 30 centimeters, 50 centimeters, probably more, that's going to be it for your stuff. You know, that's a good point. This one is semi-arid and arid regions, southwestern United States. All right. If you have areas, for example, in Louisiana, the example we were looking at this morning, you know, like I don't know, TMI was about 25 or something like that. Well, you're going to find that the depth to equilibrium suction is much less than that. All right. So this is a nice piece of work that they did together. How they did it? They went and dig and they, you know, bore holes and start measuring water contents. Water contents in January, in February, March, all the way down for a couple of years, and they figured out in the profile when the water contents were measuring, right? And if you see the graphs of all the data that they were taking, you know, there is a point when the groundwater table have an envelope and basically becomes 1, right? It's a little variability in there. When that happens, then this is the water content that is associated with a suction at equilibrium, okay? So that was the way that they were able to measure that stuff. So now you have the settlements from the laboratory that you do collapsible soil increase, and then basically you figure out what is the wearing strain on that, and then you use you use the depth. I don't think I have the depth. Okay, here we go. So the problem is, if you have all the way to 100% degree of saturation change, right, you're going to have, here is the line of the collapsibility. You're going to be, all right. So higher degrees of saturation, okay, will give you full collapse, right? Full collapse. But if you do have only like 20% degree of saturation change, right? You started with a soil with 25% degree of saturation, and you ended up with a 45% degree of saturation on your collapse, then you have 20%, and you're going to have a collapse that is much less, like 10%, okay? So you need to make sure that you understand that in the field, a full collapse, that the one that you are measuring in the lab is a full collapse, can be corrected or should be corrected by the real change in the degree of saturation that you're having in the field. All right? So this is important. That's why it's important to measure the water content, the density before and after those tests. Most common site improvement practice for payments. Usually the native subgrade of collapsible soils are soaked with water. That's what we do. That we just go ahead and just soak the, put a lot of water in there and just basically do a rolling compacted heavy equipment and just basically cause the collapse before building the road. All right. Usually sponding the water over the region, infiltrate, or put infiltration wells to do if you need to do a little bit deeper. Compact the soil and with heavy vibratory rollers or for shallow depths, or dynamic or vibratory dip for deeper foundation deposits, more than half a meter or so. Or you can do just excavate and replace, which also is very expensive. But there are some methods that we can do when we have shallow, deposits of collapsible soils. Expansive soils is another animal. Okay, this is another thing that also don't follow the consolidation, equations that we learned for consolidated saturated soils. For compressible saturated soils, expansive soils are also a function of the water moisture changes. It's not only a problem of United States, a problem of 6 of 7 continents. We got expansive soils. All right. Volume change is associated, causes a lot of distresses to the lighter structures. It sometimes might be a structural damage, but usually it's a lot of damage in cosmetic stuff, and complaints of the homeowners for that. This is economic losses, due to repairs are terrible, and the worst the infrastructure that suffers the most are the roads, because they are very light, right? Very light, and roads are suffering a lot because of that. All of these. Here we got collapsible soils. We got the blue ones, okay, and the red ones is the expansive soils in the world. Here we go. So this is the distribution within the United States. Also, you have your black soil in here, which is some expansivity, a lot of expansivity as well on that, and probably you know more than me, in which areas you can find these expansive soils in India. Here are the blue areas, the red areas. We got a few deposits in there, and we have them recognized, but the problem is we are going into those areas more and more because of the population spread out, right? What is an expansive soil? It's a soil that has the potential of shrinking or swelling when subjected to changes in moisture conditions, right? Deformations are significantly greater than elastic deformation, so you cannot use elastic or plastic theories for that. And the problem is not that you have the whole site going down are the same. The problem is the differential sediment, right? This is what causes your problem right there. And usually what you do have is the flapping situation, right? Like if you have the road in here, you're going to have the shoulders going up and down, up and down, up and down, and you see that crack or longitudinal crack forming out pretty quickly, okay? Damage caused by expansive soil, like I said, mostly likely buildings, pavements, and causes more than any other natural hazard. It doesn't kill people. That's why it doesn't make a lot of noise, right? But the damage associated with that in terms of money are immense, right? We're talking about billions of dollars in annual damage for infrastructure in the United States. Problem more associated, this is Pupala. 1/3 of the damage done to residential construction, 2/3 to roads, right? So we got a lot of problems. And here actually, Pupala and Cerato did a very nice correlation between the US population increase in millions and how the millions of dollars due to expansive soil problems also increase, okay? So as population increase, the cost associated with damage to expansive soils increase. Damage caused by expansive soils, I think the one that you will see the most on these areas are a longitudinal crack along the road, all right? So again, it has this flapping situation. Swelling is shrinking until the crack forms, right? So you're going to see that cracks close to the place when the water is getting in and out, okay? You're going to see those cracks, you're going to see those cracks, you're going to see those cracks, all the way along the longitudinal thing. There are no longitudinal cracks caused by the trucks. They're cracks caused by the soil, the environmental problems on the soil. Also significant surface roughness, right? You're going to go, and if you see soils, that are expansive, you're going to see some bumps, and there are roads that you can just see that, that thing went up and down is because you have deposits of soil that goes up and down all the time. So a lot of roughness, and this is important because that's how we measure that in pavements. Especially a problem when the deep cuts are made in a dense, over-consolidated soils as well, because they swell. Factors that influence the swelling, I'm not going to go, this is soil behavior. I'm just going to quickly just have some points in here, but the slides are there for you to check. Soil properties are important, environmental conditions, stress state are important. Soil properties, clay mineralogy, right? So you have that negative electrical charges around the clays, which will attract a lot of water, and there are different forces that are used to that. Those theories are not thoroughly validated, and all of those are theories, right? So we got a very nice tales to tell our students, but every day we talk about different things. People talking about 10 or 11 different ways of how this water gets bonded to the soil, or how it is. So there's a lot of stuff in there that Mitchell is a great, the Mitchell book, I don't know if you know the soil behavior Mitchell book, is a great, very good if you are very interested on study how this chemical interaction with the water of clays going. This is a great place to start with the water chemistry on that. But basically, this one gets into, there is a lot of replacement of cations, particle adjustments, everything just to get into an equilibrium condition. There are some clays that are very high volume change, mormonionized vermiculites. Usually, if you check in the liquid limit versus PI chart, they appear close to the A line, and the other ones, the iolite and kaolinite, are not that expansive. So we got a very high clay content, but it cannot be expansive at all. But again, I didn't bring the chemistry in here. This is a whole course that we also teach in that. A little thing for you to have the divalent cations, that's soil that contain magnesium in water, are less swelling than the one that contain the sodium, for example. Soil suction, obviously the problem is, now you understand, the problem is the change in suction, right? Change in suction. So it doesn't matter, if you have a very dry soil, you say, okay, I'm going to wet this guy and cover. That's cool, probably will remain wet the whole time. But if the soil is very dry, or the environment is very dry, eventually that soil will dry it again, right? And the structure is going to shrink, or the soil is going to shrink. So you need to be careful with those solutions of you're thinking that if you just wet it, you also can have the shrinkage going on, and it has more problems on that. Or if you want to let it dry all the way, well, it wets and it will expand, all right? So the change in suction is important, and the more suction, obviously, the more attraction of the water in the soil. A wider range in moisture contents, higher plasticity index, more swell. Flocculated clays tend to be more expansive. Flocculated clays is one that you compacted dry of optimum. Cemented particles reduce the swell, obviously, because you can mobilize them. Higher density, greater repulsive force, large swelling potential. If you see on the pavement industry, they say do not compact at maximum dry density. Compact at 90% gamma D max. For the rest of the structures, and we do a lot of infrastructure foundations, we usually try to compact 95 to 98% of gamma D max. For soil like this, you don't go more than 90%. Okay, and this allows to do a little bit more, less swelling. The environmental condition, obviously, the initial moisture condition, the climate. You need to find a way to measure the climate to put it into the models, right? Because you just can tell them, here is arid and here is wet. The groundwater table depth and the temperature. Believe it or not, moisture will diffuse always to the cooler areas beneath the pavements. So this one also causes, gradients of suction going on, temperature and thermal gradients. And we can cause a lot of problems: new construction, removal of vegetation, a lot of irrigation, aggressive trees. This is one of the things, a lot of dissertation going on right now, because one thing is that you have the suction due to the environment, but if you plant trees in there that like to drink water, okay, you're adding more problem, more stress to that one. So there are some of these models that you're going to see in the second hour that probably need to be modified by the presence of trees, all right? Swimming pools near the house, leaks, poor drainage, and fissured soil promotes more swelling because the water can go deeper, right, through the cracks. The stress conditions, over-consolidated soils are more expansive than normally consolidated soils. Repeating wetting and drying tends to reduce the swelling in the soil. We have done a lot of work on that. And this is interesting because what we do as engineers is, okay, you need to measure the swell potential of this. You take a sample, you put it in the lab, and you do a swelling test, and you report that. Well, in the environment outside, doesn't work that way. It works that, it gets wet, dried, gets wet, gets dried, wet and dry, okay? The swelling potential after 5 or 6 cycles of wetting and drying will reduce to a point, okay? Which is not the maximum one that we always give to our structural engineers or to our engineers to do the rest of the work. Greater movements if the expansive clays are shallow. It means that not only the environmental load that you have, but also the overburden pressure, right? If you have shallow soils, are going to have more prone to expand, swelling pressure. But if you have very deep soils, they actually can get collapsibility down there, or compressibility actually. The zone of seasonal fluctuation, already told about the active zone. This is important for you to this one. I gave you this work by Van and Houston that you can start from there to figure that out. Again, this is a very important and difficult thing to get. So the depth to the active zone is important that you get. And I already talked to you about that this depth of suction can go from 4 to 34 feet easily. How do you identify the soils? Okay, there are many ways of doing that. You start in the field, you're going to see cracking all over the place, right? It shrinks when they dry. What environmental conditions? If you have arid or semi-arid conditions, you're going to see more soils of that. There are expansive soils a lot also in wet conditions, but the thing is they remain wet. So there's not a problem with those. Site exploration, you need to go and check. This is all what you follow the same procedures as any other reconnaissance of any soil that you got. Okay? You go to the field, you study the geology of the place, you identify what areas can be done. You do visual observations, cracks around, determine the ground moisture conditions and where the water is going to be going, and other site information. You interview local engineers, interview George. George is the guy that is always working in that company. He's not even an engineer, but knows the area very well, right? So you go and ask everybody for questions and for people that know the area. Always ask questions around, okay? People know the area. They know what's going on in there. If you are getting there new, ask questions, okay? There's nothing wrong with that. You learn a lot. And this is important because you also use the experience from local practitioners that, like I said, might not even be engineers, but they're very good and they know what they're doing in the field. How to determine how expansive is your soil? Visual, again, inspection, check for fissures, for cracks, check for clay content. How do you check it? Put water in there. If you see that it's soapy, okay, you get this soil in the lab because it's going to have clay right there, right? There are some other evaluations, qualitative and quantitative. I don't go to those, but there are many. They're very simple one like this. They use activity, for example. Activity is the ratio between PI and percent clay. They can use that. Or they can use, for example, liquid limit, the SPT, the end value, okay, that you get from SPT samples, and probably expansion, swell pressure, and swelling potential for, percent passing different number to 100. So these are guidelines that will take you at least, okay, I should do an expansive soil test right now, okay? That's what you need to do. Semi-quantitative evaluation, this is a very simple expansive test. You put the soil in there and you figure out how much will expand on that one. This is very done by the agricultural people all the time, right? We do also expansion index tests, the response to wearing tests on the odometer, correlations with other index property. This one is 2006. We got a lot of soil, like 300 soils from the area. We got PI passing 200, liquid limit, all of these parameters. This is very empirical equation. And we were able to get the swelling potential, the free swell out of and we put together all this data and we found the R squared is not, anything for us in geotechnical R squared of 0.5 or more. He said, yeah, that's great, right? Structuring engineers will kill us, right? But for us, that's not a bad and not a bad correlation. So that means that you do have means to figure out if that soil is expansive before getting into all these, testing requirements. And this one is based on WPI again. Every time you see WPI, you see that is me going around because I love my WPI. This is the odometer tell again. We have summer programs when we get teachers to teach the students in the high schools. And we give them a little bit, a cell or something, and they do, with a little dial gauge, and they do swelling tests all the time, so you can do that one pretty easy. Again, you apply dial gauge, you get the sample in here sandwiched between porous stone, and you saturate. This is something wrong with this picture. Do you know that? About the water level. Well, if you want to saturate something, you don't put the water all the way to the top, right? You're going to trap a lot of air in there. You're not going to saturate anything. You have to put the water in here, so you get the water all flow from below, right? Don't get, you don't inundate a sample. You're just going to put, so there's something wrong with that picture. This is the STM standard D4546. That is the one-dimensional swell or collapsed soil. We measure swell pressure. We measure the free swell. So we got two ways of doing it. You go ahead and you do your sample, okay? Then you inundate it first, and measure how much will swell all the way to 100% saturation. And then you start loading it, loading, until it comes back to the point of zero swell. And that's your swell pressure right there, okay? That's the free swelling test that we call. And we also have the constant volume test, which is a little bit more complicated. This one can be done in one sample. I like to do it different samples. Sometimes loading here and I do it, then loading here and I put a point in here and loading here. I like that better. I don't know why. Because I think it eliminates the stress history because I already loaded to this thing. I already weighted to this thing. So I do a multiple samples in there, but you can certainly do it in one sample if you need that. So you're going to have all this data there. Once you have the strain, okay, you do again the summation, the strain over the heights that you're going to need it, the height in the field. And again, we correct that value because we believe that the swelling test in the lab is the most conservative swelling test, right? You're going to have a number. And this one is going to be a function of the degree of saturation that actually is going to be changing. All right? So that's how we do it. Preventing measurements usually is practical. If you have a depth of about 3 to 4 feet, you may want to remove that soil. You don't want to deal with that soil. We do it. If you can't, you can also do kind of a horizontal barriers. Pretty much, you get the shoulder a little bit wider. So you have the water to get in, before it starts evaporating. You don't give them the time to get down the structure, down the pavement, right? So you kind of do that. Or you can also do vertical barriers. So for the water to have more time to get into the pavement structure below. So you can do barriers. And this one is the partially encapsulating along the edges or full encapsulation when you do the vertical barrier all the way down. You can scarify, stabilize, and recompact the upper portion of the expansive soil. And the most common thing to do for all these state roads is lime stabilization. Some people use cement for clays. I think the best thing to do is lime. It's usually the most way of doing. Cement is not that we don't do it, it's just not very accepted. I don't know why. But cement is more doing for grouting, for other, other stabilization, or more granular material. Lime is more for the kind of the swelling. And it reduces the swell potential, the shear strain increase, moisture content is decreased, and we usually put it in there like with no drainage around it, like impermeable material. And the resilient modulus for those soils, increase probably 3 or 4 times. All right, so that's how we do it. So we don't consider flow-through treated materials, what I'm saying. And I'm saying that because it was a question this morning about that. All right. So soil stabilized material, like cement stabilized material or lime stabilized material, we consider this to be kind of an asphalt layer or concrete layer, right? And we deal with that way. Not like a soil now anymore. Pre-wearing, surcharge. Okay, surcharge. You say, what if I load my, I do a surcharge like we do for consolidation? Well, that might reduce the swelling pressures, but, actually will be okay if the swelling pressures are small. When you have large swelling pressures, that thing doesn't work. That doesn't work. And again, pre-wearing the soil is okay if you know that the soil is, the environment is going to be wet all the time. If not, it's going to dry anyway. And if it shrinks, it's going to have the cracks formation. So how we consider that in pavement design? That's the interesting. Okay, how, if we know the road is going to have expansive soils in some areas, so how we consider that? This is very empirical, the way we do it these days. Okay, where we do it. And again, this is going to my pavement engineers in the room. We need a little bit more, and we're going to talk about tomorrow about ways of doing a better job for this one. But this is what we do. They base this in the roughness index. There are 2 ways of measuring the roughness of the pavement. One is the serviceability of the pavement, and there is kind of a smooth factor that they do for that, or they do a roughness. And the roughness is nothing but the elevation. I'm going to go to the IRI in a minute. The elevation variation that exists in the pavement that cause variations in the vehicles. When you go, right, you feel that roughness on the vehicle. And there are variables that can quantify that roughness. So they said, they said, if you have expansive soils, your road is going to be rough, right? It's going to be more rough in here than there. And what basically they do is they said, okay, we're going to be putting that and affect the International Roughness Index, which is one of the parameters that I was talking to you this morning that they use as a distress. Thermal cracking, longitudinal cracking, rutting. The IRI also start like, the roughness when you time equals 0 and, 30 years. And you start more rough, this. And there is a point when it comes that they always said when you come to this point, do rehabilitation on the road. Okay, they put some surface layer and they start again, right? When it comes in here, they do rehabilitation again. Okay, and there is a point when they said, okay, the road needs to be replaced. So this also is a function of time. How they calculate the IRI, or the International Roughness Index, is a cumulative vertical deviations over a section of road per unit length. So how many inches going up and down per mile? That's what they do, right? And they do have a profilometer in a truck that they just go on the thing and they start measuring how much goes up and down, up and down, up and down, and they start measuring that. So for 1 inch, they measure how much is the height, so they measure kind of the slope, right? And they make the accumulation of that thing to figure out what is the roughness of the road. Typical values are 25 to 40 inches per mile, okay? Or when the road is super rough and it just need maintenance, it's probably 250 to 480. So this is the equation that they use to do this line with the time. This is the International Roughness Index, and they use the initial value. They usually after construction there is a value, and there is an empirical equation that has a psi factor that I'm going to explain to you in a minute what is this. This is an important one for us. They have this one is HMA, this is asphalt, this is fatigue cracking, thermal cracking, and rutting. All the distresses that you have in the pavement. And they basically associate or correlate the roughness with the summation of all those distresses, right? Well, let's look at the psi factor. Psi factor has, it's a change with time and has two parts to it. One in here has the precipitation, freezing index, and the percent clay. This represents the roughness due to the frost condition that we're going to see next. The second one has precipitation, PI, and passing 200. These factors represent the high volume change that you may find on the road. That's how they measure that. It's very empirical, as you can see. Very empirical, right? So we need to do a better job, and we're working on that. But this is what is being done forever. And actually it's done forever in the whole world. So it's an empirical measure of the roughness. And basically what they said is, if we have high PI and high passing 200, right, we're going to have high expansive soils. And we got more precipitation, there's going to be more change in this one. All right. So there are equations like the IRI for everything, for plain concrete pavements. And again, the psi factor appears in here. Psi factor right here. Okay? And the psi factor again in here is a couple of factors. This is a function of freezing index, and this one is the passing 200. Okay? And so forth. So this is the way they are considering the expansive potential of the soil in the pavements right now. So give you ideas to improvement, right, of the profession. Alrighty, how much time you have? 3:25. Have 5 minutes for frost heave? I'm in trouble. All right. Last of the soil that I wanted for you to know a little bit about are these soils that that has a problem with frost heaving, right? And again, that's going to require a lot of big theories, and actually perhaps this is one of the best things we have done on pavement analysis and design, okay? Because if they are able to figure out the temperature with depth, right, they should be able to figure out how much frost depth is going to be right there, okay? And this is problem number 1 that they have solved. And the problem number 2 is how much, if the soil is susceptible to heave, how much will heave, all right? So it will require, obviously, now thermally driven moisture flow. Okay. So let's talk a little bit about that. We talk about ground freezing, and I'm going to have to go pretty quickly on that because I don't have time. So the main effect is frost action, the temperature effects. Okay, so we have been talking the whole day on moisture effects, right? And not on temperature effects. So this is the second very important parameter on the environment, the temperature, right? Temperature. Think is temperature doesn't move water if the water is unfrozen, pretty easy. Okay, the gradients, suction gradients, gravitational gradients are much higher. But thermally effects on soils when there is frost action are big problems. They heave during the winter, okay? And they reduce the subgrade strain due to the thawing process, one of the questions we have this morning. Heave is more critical for flexible pavements. Rigid slabs, usually concrete pavements, do not allow differential heave. And the problems when you start getting to the differential heave that you can see on this drawing here. Okay. Differential heave will cause the roughness that we were talking about in a minute. Highways, roughness is controlled by decreasing the speed. But what do you want to do in an airport? You know, you need to also think that all the things for pavements also apply for airfields, right? Well, you cannot slow an airplane, okay, going in or out, right? So that's why it has to be absolutely smooth. You have to have a very absolutely smooth surface, right? So airplanes must achieve certain velocity at takeoff, and they cannot afford to have a roughness due to the expansive soils. Differential heave is then critical in the airfield runways, okay? And that's why these theories have been developed for that field more than anything. Pavements, we use that IRI, right, that you just saw, and you saw the other part, right? Very simple. But the airfields have a little bit more of theory behind that because of that. So thermally driven flows in saturated soils are rather small. However, when you have unsaturated soil can be large and are important in applications like subgrade stability, swelling soils, and heat transfer and storage. You heard from your professor yesterday or so about the Philip and Debris developed for the theory of the couple of heat and moisture flow, and it accounts for both the liquid and the vapor phase flows on that one. So the vapor phase is one. The liquid phase is another one, okay? And you need to figure out what you need for solving the problem. For when you have vapor flowing through a soil, you're going to need temperature gradients and moisture gradients. When you have liquid, you're going to need temperature gradients, moisture gradients, and gravity, all right? Moisture gradients and gravity. And I'm going to go to that a little bit later, okay? So these are the Gordon equations. Again, I'm not going to go very in deep on this one, but you have a amount of vapor flux that is going to be a function of the thermal gradient and the moisture gradient. When you got the flux of the water in here or the liquid, you're going to have the temperature gradient, moisture gradient, and the gravitational gradient. So the three of them, right? For those, you need the constants, or to figure out. So the constants are going to be. This one is going to be the first one. This is going to be the thermal vapor diffusivity, okay? And you're going to have in here, this is the thermal and this is the isothermal for the water content, diffusivity. It's just to give you a little bit of idea of that, how many factors you're going to need. And this one is other diffusivity for the liquid, the thermal liquid diffusivity. And this is the isothermal liquid diffusivity. And I'm done with the time. Sorry about that. I'm going to have to give me another 10 minutes. And this is the unsaturated hydraulic conductivity that you all know about that one. This is the vertical direction. So for all of these diffusivities that you need in that, or those factors of correlation between the vapor flux and the temperature gradients and the moisture gradients, all of them, I'm just gonna, very quickly that these are either a function of tortuosity, air content, relative humidity, and temperature. The second one in here, the isothermal for the flow of the vapor, is a function of the tortuosity, relative humidity, suction, head or water content. And the ones on the liquid, you already know that because you see that in the morning, is a function of unsaturated hydraulic conductivity and the suction and temperature. And the second one is a function of the unsaturated hydraulic conductivity and the saltwater characteristic curve. All right? So all of these we need also to solve these equations. All right. So, as a summary, we need 4 relationships to describe, which are the permeability, the unsaturated hydraulic conductivity as a function of moisture content or suction, the thermal conductivity as a function of water content, the volumetric heat capacity, and the saltwater characteristic curve as a function of volumetric water content. And obviously, you got parameters, you can measure them in the lab, but also you got a lot of parameters depending on the soil material, right? So thermal conductivity properties are available for air, water, ice, for all the materials, soil, shell, different rocks and stuff like that. Heat capacity as well on that are also available. Volumetric heat, you're going to need latent heat as well, heat of evaporation, and I wish I could go a little bit further in that. But there are equations that are also empirical that relate, for example, the dry density and the water content in order to get the volumetric heat, okay? For frozen soil, and so forth. So those are the values that we use. The heat of fusion, you're going to need. Heat of vaporization, you're not going to need it. So thermal conductivity for frozen soil and frozen soil are also available. These are all properties that can be measured or predicted. This one, for example, is a function of if it's a sandy soil or a silt or a clay, and it's also a function of the density, I believe. Densities, so you got density variation in there, and that will give you the thermal conductivity for the unfrozen soil. Also, there are thermal conductivity graphs for frozen soil. And basically, all of these will help you to run all these models that will give you what is the temperature gradients that you're going to find on your soil, okay, because of that. So I don't go through that in detail in here. And again, it requires a transient heat flow analysis, again, to solve these equations. And important 3 topics that are depth of frost penetration, frost action in the soil, and the effect of freezing in soils after thawing that you need. This is the depth of frost penetration. The phase change, you are going to have a phase change between liquid and water, right? The temperature in here below 0, after 0. This is a Newman 1860 analysis in which you, at a particular water content, the thermal energy with respect to time is equal to a constant, which is your volumetric heat capacity. That's where you need that guy right there, right? So you guys know more about thermal energies than anybody else probably here. So you do have some models that consider the latent heat, just to get the energy just by the latent heat. Some of them, the changes in the volumetric capacities of those soils, and the solution depends on that, okay? This is the Fourier equation, that's the heat flow analysis that you're going to need. And here is your thermal conductivity here. So the heat flows, and this one is the temperature right there. All right. This one is the latent heat of fusion. It's the amount of the thermal energy you're going to need to absorb, to be absorbed or evolved for 1 mole of substance to change the states from a solid to the liquid or vice versa. This is the continuity equation. You have to have continuity equation. You have to have conservation of mass, right? So, and this one is the 2 principles must applied. And this one will give you the one-dimensional case, for example, if you have the absence of freezing or thawing. This is the change in temperature with respect to time. This is the change in temperature second derivative. This is the alpha that we were talking about in here. I don't know why I ended up in the other slide. That's the one-dimensional transient heat flow equation that you need to solve. Solutions, because I'm not going to go through that. This is the thermal diffusivity here, the alpha value that we were looking at yesterday. And these are the continuity equations. You got it in there. For you need the permeabilities for frozen and unfrozen in here, latent heat in here, and the solutions that we have. Just to round it up, there are a couple of solutions that the airfield engineers use: the Stefan formula and the modified Berggren equation. One of them assumes that the latent heat is the only heat that was going to be removed from the soil in here, and basically this is the equation, and that's going to give you the frost penetration, so the solution of that. Function of the frozen permeability, and this integration in here is your freezing index, is the amount of time that you're going to have the temperature below 0, okay? And you make the integration of that. So basically, this is the time, and this is the temperature, and below freezing. And this amount of days that you got freezing temperatures is your famous freezing index that you're going to find in all of these equations that you get. So this is one of the solutions. It's just, this. And the Stefan, no. And this one is the solution for the modified Berggren formula. Has a parameter in here, which is the lambda, is a correlation coefficient. Again, get the average thermal conductivity for frozen and unfrozen soil. And here got the temperature lower than 0, and the time, and the latent heat right there. So that's a closed form solution. This lambda, you get it out of a couple of graphs. This is the coefficient, the correlation coefficient is a function of the fusion parameter and the thermal ratio. And those are the fusion parameter. The thermal ratio is nothing but the temperature above freezing and the temperature below freezing. And the fusion parameter has to be with the heat capacity, the latent heat, and the temperature on that. So all of this is already there. Closed form solutions are available to those equations. And this is one of them. So if you want, we can probably stop for you to have any questions in there.
It's serious tutorial. If you want to extend, or if you don't want to take a break, it's fine.
No, I'm okay. I'm okay. I just finished it here. I just feel like I'm going too fast, but But have you been able to figure out everything? Because I'm going too fast. I'm trying to get all this. So the last thing is the frost heaving, right? So one thing is you got the frost penetration, which is great, but some of the soils heave. And that's the problem that you're going to find. They heave. So the problem with the heaving is that the freezing of the soil might make formation of lenses of ice, okay? And that only occurs in few soils, okay? And I'm going to have the spoiler in here. There are no sands, there are no clays. There are no sands because the water can go in and out quickly. For clays, the water, it goes slowly. And that freezing, that formation of the lenses depend on the cooling rate. If the cooling rate is too high, there is not much heave, as the water cannot migrate to the ice lenses. If the rate of cooling is low, the soil is susceptible to frost, okay? And if there is water available, like at any water table or perch water, frost heave will occur. in order to have frost heave, you're going to need frost susceptible soil, you're going to need freezing temperature, and you're going to need water. Okay, if you have those three conditions, you got the frost heave occurring. Okay, again, there are driving forces, are the equivalent hydrostatic pressure gradient caused by the removal of the liquid water. So you have the front of the frozen soil in here going, and that creates a suction. Okay, actually a frozen soil is like a drier soil. Okay, it creates a suction and trying to bring more and more water into that. And the second one is an osmotic pressure generated by the high concentrations of ions in the water adjacent to the ice front, and the interfacial tension between the water and the ice. So there are driven forces for this water to be transported and form the ice lenses below that made this soil heave, right? So again, when the suction increases because you're driving this water into that, the suction increases, freezing will reduce the hydraulic conductivity, all right? So clays can withstand higher suction values, and therefore the hydraulic conductivity doesn't get very affected because of that. So if you want to see here, this is the comparison between the clay conductivity, the sand conductivity, but look at the silt where it goes. So silt has the capacity to get the water in at a certain rate that those ice lenses will form. And the silt material is the one that you're going to have to be very careful with, all right? Clay, like I said, is that. These are methods that get the estimate of the rate heave empirically. You have different soil types, and this is the percent passing 200, and this is the average of heave. If you see the soil that heave the most are silty material, okay? Here there are some clay, link clay material, and you get into here more sandy materials in there. But silts are your problem, okay? Soil that have more than 3% of particles, finer than 0.2, are potential for frost susceptible. And I already talked about the sand freezes homogeneously with depth, no problem with frozen. In here, clays also, but the silts are the problem, so you're going to have in here. This is our U.S. Army Corps of Engineering that classify the soils as a potential frozen condition. This is the worst, and these are the silt, very fine silty sands, clay with pI less than 12, and some other clays that are layered. Okay. How do you mitigate frost heave in pavements? Well, you basically increase the thickness of the granular base material. So what happens is you calculate the frost depth, right? You can have all these differential equations calculated. And if you figure out that the soil is going to be frost heaving, okay, what you do is you put more granular base material on top, all right? So the depth of the freezing doesn't get into the soil that is susceptible. All right. So this is one way. Or insulating the subgrade of the soil. Geotextiles have been used for that, and we're going to talk that the last day. Or reducing the water content by drainage. Okay, if you don't have source of water, then it's not going to be happening. Okay, two methods for the design. One is the limited subgrade frost penetration, like I said, requires a sufficient thickness, and there are graphs and tables when they said, okay, if you have this depth of frost penetration, increase this guy by this amount of inches. And the other one is the reduce the subgrade strain. Basically, is assuming that the subgrade is going to reduce the strain due to that at a particular layer. Right? And then you calculate with the two methods, and there are graphs and figures when you calculate, and you figure out which one requires the higher values for the granular base to be increased, and that's the one that we use. That's why we got such a big increase the granular base materials in airfields. All right. On road considerations, you already saw that one. Is again, this one is for airfields, this one is for pavements. We consider the psi factor in here. And this is the freezing index. And that's considered very empirical as well. And we did a good job on doing that, but we're going to see that tomorrow, I guess. Doing a better job on that. All right, I made it. All right. Any questions that you may have on this? I know there's a lot of stuff in there, but at least I wanted to have the idea, okay, of the problems you're going to find and the ways that there are solutions and there's stuff like, this material is being collected for many, many different sources and information. So it's difficult to find everything in one place. So this is, good sources of information for you to keep. Any questions on that? Yes, sir?
Yeah. Yesterday, while explaining experimental methods to determine the flow through unsaturated soil, so you mentioned unsaturated coefficient of permeability, but today I saw a couple of slides you mentioned about unsaturated hydraulic conductivity.
The same.
Are they just same in terminology, or are they interpret different things?
No, I apologize. It's just I use different sources of information, and depends on that. I made it. But
Yeah.
unsaturated hydraulic conductivity, which is that the one that we use from Darcy's law, right? The one that the coefficient of that we use. This is the one we use. Intrinsic permeability, which is meter square, we don't use that one.
Yeah.
So it depends. Depends on the source, depends on the person. But we usually use coefficient of permeability indistinctively with hydraulic conductivity. But hydraulic conductivity is the writer. But it's the same. The one that we've been talking in here is the hydraulic conductivity all the way.
Yeah.
Whether I call it coefficient of permeability or hydraulic conductivity.
Yeah, while explaining yesterday, like experimental method,
Yeah.
so you mentioned coefficient of permeability.
Mm-hmm.
You took that word more than hydraulic conductivity. That's how.
Right. Is this
I just want to clarify.
Exactly.
Yeah, that's all.
Sure. Yes.
I
Question?
Hi, Prof. So, Kim again here this side.
Hi, Matt.
So, I would like to ask two questions. One is pertaining to this section for the frost heave and sweating. The other one is from the expensive sweat. So, for first one, like when we are considering the effect of frost heave or thaw, mainly considering the effect of thaw. So, suppose we are modeling in any of the FEA packages software. So, which considering modeling is going to be suitable? Meaning, like if we consider the effect, considering Mohawk lumps on any particular model, so how to include those effect of thawing when the temperature is increasing, means there will be some generation of water pressure. Can you please explain about this?
That's a good question. If I understand well what you're saying, okay, we do have thawing, and thawing creates water, okay, water in the soil that are there, that might increase the pore water pressures in the soil, all right? And if the pore water pressure in the soil increases, they might decrease by effective stress, right? Because we're talking about saturated soil conditions, right? So how my effective stress, which has higher pore water pressure in here, because the water is just dissipating after, it thaws, and before draining out, right? It's going to be that excess pore water pressure. Is that correct, Emma?
Yes,
Right.
correct.
So how we consider that in design? Okay, how we consider that in design? That's a very good question. For payments, again, we don't use the shear strength of the material. We use resilient modulus, right? The resilient modulus. And basically, we don't consider the effective stress will, affect directly the shear strength of your material, right? Which is going to be equal to C plus sigma tangent phi, right? So this one might affect the shear strength that you use for the stability of the embankments of the road when that happens, right? And this one, basically you may have to evaluate on the thawing periods, okay, a reduction in the shear strength, which is going to cause the factor of safety to go down, right? And it might cause some stability problems. But for the pavement design per se, again, we don't use shear strength at all. We use resilient modulus. And the resilient modulus get affected also by the thawing conditions. But what we do is we got, let's say this one is the resilient modulus that the soil has on the unfrozen soil, right? The unfrozen soil condition. And that's the equilibrium condition that you got. And obviously there is the environmental effects that cause, this one goes down and up seasonally, right? But in reality it goes into an equilibrium condition. That's what the theory, trying to do. So you got the frozen occurs. So what we do in design actually is very empirical. We get this resilient modulus and we jump it. We put it out to, actually the resilient modulus for very frozen condition can get into 1 million PSI. When we have it here 30,000, 40,000, okay? And it remains frozen for the duration of that thing, and then it's thawing, start making the thawing, right? And that thing goes down, and it goes all the way down to probably half of, depending on the soil type, to half of the resilient modulus, and then drastically recovered, and the time of recovering period is also a function of the soil properties. So if you see, it's very empirical, and it gets into the equilibrium condition that start getting again affected by the environmental, the infiltration or evaporation. So this is how we do it. And this one is connected to, again, the time series for rotting, for thermal cracking, for fatigue cracking, depending on the time. So there are no considerations of shear strength reduction per se. The considerations are on the resilient modulus reduction. And there are empirical equations that reduce this value to a point depending on the soil type. And usually it's between one third of the reduction to 2/3 of the reduction on that, on the environmental equilibrium condition. So that's a good point, but this one goes into a different analysis that you have to do for the embankment stability of the roads. And we're going to see a little bit more on that later on, but that's what I explained this morning, I think.
Thanks, Prof,
You're
for
welcome.
answering the question. So I have one more question. Like
Sure.
on the slide number 24, you have mentioned about there is no specific continuity model we have available. Just a moment, I'll go to that note slide. I think 24.
That's for
Yes.
expansive soil or for?
This one is 6. Just a moment.
I don't see the number of the slides in here.
Yeah, like in the definitions we have in the third bullet points, deformation are significantly greater than the elastic deformation and cannot be predicted by elastic or plastic theory. So suppose if we have to simulate this.
Yeah, what I tried to set in there, and okay, I think that's
going to be suitable, like we have generally Mohr Pull-up and Ducker bracket model. We go for the pavement just to include the linear increase in the linear stiffness. So which model we should use for this particular case?
for expansive soils. I'm sorry, I don't understand what you're asking me.
Did I go audio?
Are you talking about expansive soils? I cannot hear you. Is he gone? Oh, okay. So he hung up or we hung up on him? I don't understand. I'm sorry. I don't understand what he was asking. Did you guys understand what he was asking? Anybody?
Ma'am, for expansive soil, slide number 3, there you have mentioned that the deformation is significantly greater than elastic deformation and cannot be predicted using elastic or plastic theory.
Correct.
So,
That's what he was referring to, right? And that was expansive soil, right?
yeah.
So what was his question?
So if I want to estimate the settlement, then which model should I use? You are asking.
Okay, okay. For the expansive soils?
Yeah.
That's going to come tomorrow. You're going to be happy to hear that. Actually,
same
like I said, for payments,
This
right
one.
here. For payments, what we cannot just use the consolidation theory. That's what I try to say in here. You just can't do that. All right? The changes are not within that range. So in payments, what we do is we use that international roughness-stiffness, very practical, empirical equation. We put a value in there that will add to the roughness, and that's pretty much it. So this is too bad. This is too bad. So tomorrow you're going to see a model that Austin Olay, one of my PhD students, put together about 4 years ago. Almost got a prize because of that. You know, it's an amazing model that he put for, you know, it could be for any condition when you do have access to the environmental changes, like a payment or a slab on grade or something like that. And that model, I'm going to be explaining to you tomorrow what we did on that. It's a little bit more complicated for sure than what they did in here. Right? But we can apply this to the IRI. Actually, the real model we can apply to the IRI, and on an empirical basis at the end. But at least the model is mechanistically rigorous, and we can do that. So yes, tomorrow I'm going to be. I mean, if you're still there, we're going to be working.
Yes, I'm here.
We're working in a model to estimate expansivity for payment design. Okay, that will replace pretty much those, that equation that we had for the psi factor in there. All right, or it's not going to replace the factor, but it's going to be finding that factor in a mechanistic, rigorous way. Okay, so you're going to see that tomorrow. Okay.
Sure, ma'am. Thanks.
You're welcome.
Hello, madam. Yeah.
Yes.
Ma'am, here.
Yes.
I have a couple of questions. First one is related to the heaving that you have explained related to the freezing or frozen of soil. So there you have mentioned the suction is increasing. Suction increased when the soil is frozen.
Yes.
So could you explain a little bit more how the suction increases?
So I went too fast in here. I was mortified. But it's in here. So again, what we need to understand is that the frost penetration always occur when the temperature start getting down, right? So what basically the first thing we need to do is to figure out what is the temperature profile, right? In order to figure that out, you need to solve, the equations for that thermal gradients equation, and then you find your temperature profile all the way down. When you get into the zero, everything that gets into the zero, we assume that the water freezes, right? Water freezes, and therefore you do have that profile, right? So now we're talking about, you got this one, and the soil might not freeze. It's just a granular material. It could be any clay material and thing, and it will not heave. It will not heave. It will just froze, and it will thaw. It will reduce the resilient modulus, but the problem is when the structure start heaving, because it start creating cracks all over the place, and the problem, right? And for that to occur is because it start getting the ice formation below that, the ice formation there. And I guess I spread pretty quickly also, the ice formation will form because you have different gradients in there that are gonna be contributing to that movement of water, to those ice lenses to form. Now, when you get the water to be frozen and to be driven into the ice lens, the soil is going to reduce the water content because the water is going to go into that lens. Okay? If there is water, the water is going to be going in there and it's going to be freezing and it's going to be becoming part of the ice. Okay? And now the soil is going to be having reduced water content. And there is going to be, actually, there are solutions for this that imply that, you know, if we use the soil water characteristic curve, when we do the suction versus water content, okay, there are solutions that imply that the suction is also forming when you have the temperature changes. All right? It's like that soil water characteristic curve. When your temperature increases and you're driving this water into the ice lens, the water is less and less and less, and now you're creating suction. So let's see what we find this in here. Okay, so when the water is being brought to the ice front, okay, that creates the highest stress. Actually, it's like an effective stress, okay? That due to that, the decrease in the pore water pressure that you have because you increase the suction. In here, it's going to be a little bit better explained. As the negative pore water pressure increases, because you know you are removing the water out of that soil, okay, the freezing will reduce the hydraulic conductivity, and now we're going to have less water going through that. Now you do have, instead of air, you're going to have ice, right? And the ice will not conduct the water through, and now
Okay.
you're going to have a reduced permeability to do that, right? So that small suction that you have in there will be enough for water to drain if you have a sandy soil. Okay, you got a small suction, so that thing goes down easily, fast. But for
when
clay,
here,
not.
when you say this suction, are you referring to the suction of the soil, or you are talking about that ice lens?
I'm talking about the suction of the soil,
Soil.
near the ice lens.
Ice lens.
Near the ice lens, okay. And the one that is bringing the water into the ice. Okay. What do you think? Yeah, I reduce this a lot. I need to get more information for you on that. Yeah. But this is basically what it is. Once the water is attracted to the ice lens, okay, the soil starts getting kind of desaturated because the ice lens is going to bring the water in, okay, and start creating that suction around the ice lens. Okay, that's going to be bringing more water in if it has. Obviously, if you have a small suction and you have a sand, right, the water might be draining out instead of getting into that. Clay is going to be very slow bringing up, but the seal will have enough permeability, and if there is water available, the ice will fall more quickly.
One more question. This is related to the field test on collapsible soil. If you please can go back to that
Sure.
slide. We have talked about the depth
Well,
of.
I lost my glasses because of that. Yeah.
No former. The depth of equilibrium suctions you discussed, right?
Oh, okay, so this one is the field test
Yeah.
that you put just some soil in there, and basically, once we got the strain, right, the strain that you get,
Yeah.
or you got the deformation that you get, you need to figure out what the deformation is, what is the height that you have.
My question is related to the equation that you have presented here. One equation for the depth of equilibrium suction.
Okay, here we go. Where do I have it? Right here.
Here, this one. As per my understanding, the depth of this active zone or equilibrium suction, so that is also highly dependent on the soil type, or
Well, you will think, but they didn't find that.
Okay. And what is the range of the soil properties that you have used for this particular fitting?
Those were, that's a very good thing. Those were soils that were susceptible to moisture changes, but most of them were expansive soils.
Expansive soil.
That's a good point, because it might happen that this depth might be just for expansive soils. That's a very good point.
Okay. So here one more question. Now when we talk about the wetting depth, do we keep it equal to this depth of equilibrium moisture, equilibrium suction, or we go beyond that?
No. No, we don't do that. Okay, so if you have the field test, right? And you just basically what we did is we wet the soil, we put a lot of water in here, right?
Yeah.
And the water, let's say, infiltrated all the way to this front, right? And form a ball of water like that, okay? So below this we put a dial gauges, to figure out how much this thing was gonna collapse on doing that. We measured the collapse in here, and then we dig and we excavated the soil, and we figured out how much of the soil have gotten wet.
Okay.
So we used that depth, okay, the depth to multiply by the deformation that we got. Okay. So we said this was the original depth was this, right? And now we got this one, so we have a change in the vertical or height divided by the total depth of this one, so you got a strain in there, okay? So here is your collapse. That's how we calculated that. What I'm saying is, okay, you do have that strain from the laboratory,
Okay.
or from this test, and now you want to apply it to another place, right? To another place, all right? So for that, you're going to need probably to know what is the depth of the wetting on that one, okay? If you consider that that's going to be because the rainfall is going to increase on this one, you might use these equations with that and just get something that, but if not, you just need to figure out what is the depth of, wetting that you're going to be expecting, okay? So what is the collapsibility? We got the strain, and we said, okay, there is a pipe in here 2 meters down, right? And if that thing breaks, probably it's going to be wetting 1 meter down. So it's going to be 3 meters down. And we're going to be using that one because the soil between 2 and 1 meter, 2 and 3 meters, is going to collapse. So we're going to be using 1 meter. So you need to figure that out depending on the stuff that you have. In this case, I put this in here in terms of, okay, you're going to need to know what is the extent of wetting. And it might be related to the environment. But
Okay.
not necessarily
I'm,
needs to be used.
yeah, I was wondering how this depth of equilibrium suction is relevant in this case. I'm trying to relate to it.
Yeah, probably just for infiltration and rainfall.
Okay.
Just for infiltration and rainfall.
Okay.
Yeah. And another problem with collapsible soils is the following: is that you can do partial collapse easy. Like, we can do something like that because we find out that some of the soil will collapse, some of the soil will not collapse. But it's very difficult because once you start getting water into the soil starts collapsing in one side. And then you measure the whole collapse, like happening in the whole depth, which in reality, it was just one part of it. And what you do have is something that is not easy to quantify. Collapsibility is difficult. Okay. Expansivity is a little bit more because you can equilibrate the soil at a particular water content. Collapse is not because it occurs instantly. So it occurs at certain water content, but not enough. Those are great questions, and I may question this graph for collapsible soil from now on. That's a great question.
Thank you, ma'am.
Yeah, sure. Great. Love that.
And just
Yes.
question on this slide only, like, how can I physically relate this TMI? Say if you are telling that TMI is 0 or TMI is minus 50, then how can I relate it, what is happening actually in the soil properties?
Okay. Okay. This. Let's see. Okay. So I'm gonna look at that. Okay. We could. why we don't continue, like we have 5 minutes break and we continue that, and when we get into the TMI, we'll talk about that, okay, in a second. It's gonna be there in a second. So let's have 5 minutes break, okay, and we just go back to the tutorial, which is have to do with the TMI, totally, all right, and then I'll explain that. Is that okay? Sure. All right, guys, 5 more minutes, 5 minutes. Forte. What time did you get out yesterday from here? You did a better job than I am doing on the timing?
I left by 4, so I think they can.
Okay, so that's good. They own us half an hour, right? All right. So anybody need a bathroom break or something? Please go ahead. 5 minutes break. basically, what we're going to try to do is, and this is, like, I didn't want to, well, it is a lecture, but I wanted for you to just, quickly, I'm going to just show you quickly the steps, okay, to consider environmental effects on the material stiffness. We saw a little bit of that this morning, right? Now I'm going to show you every single step we follow. And again, it's a mechanistic empirical method. That's how we do it in payment analysis. But I want you to know what the questions were, how we can get that one. And I want you to be curious about other methods or some other way to do it. But, so here we go. We're going to be doing, let me starting here. So we went today or yesterday, I don't remember, I think today, I told you, okay, we have different methods to estimate the climatic conditions in the prediction of the stiffness. One which was the effective stress approach that I told you I don't want to use that one, that's Bishop, right? And there are many literature with that. The second one is using the factor that takes into account the contribution of matrix suction independent of the traffic, right? That's the example that you saw this morning, right? And the third one is considering the resilient modulus a function of the complete stress state, that I show you the big equation with the Z1, Z2, Z3, Z4, or Z1, Z1, that you said. But so we're going to be focusing on number 2, on this one. The factor that considers the contribution of the suction independently on the externally applied pressures. And you saw this one that I got from Plaxis. Okay, but you didn't see how I got this one. The only thing you get from Plaxis are going to be your suction profiles, which is going to give you those degrees of saturation profiles. Okay, and then I briefly show you the equation to get the environmental factor, right? But in order to get there, okay, there are ways of doing empirically. More empirically, okay? Don't have to run Plaxis for that, all right? And this is what actually the AASHTO design guide, which is the latest design guide that we use, is the way that they're doing it. They're not running Plaxis, they're not running final element modeling, they're doing empirical modeling, okay? And I brought this one because I know we have the practitioners in here for railroads and also for payments. So this one is part of the model, the climatic model we put together for that design guide. And that was a word that we used to call MEPDG, the Mechanistic Empirical Payment Design Guide. And that's, again, the latest that AASHTO basically adopted as the latest payment design guide in the United States. And it's been implemented in every one of the states. Probably half of them have already been implemented that. Half of them still use the AASHTO 93 way. So I want to provide the input parameters for you to follow that climate model. Like again, it's empirical model, right? It's empirical, but it's based on mechanistic principles. I will provide you the models. And what you want to do is to follow this procedure to estimate the modulus for 2 different site conditions, let's say I'm going to give you that, and 2 different soil types, and see what we get. Okay, and see what we get. Then we can analyze from how to Friday, briefly analyze what you get. Okay, so we're going to divide the group, and you're going to do exactly the same thing, but you're going to be using different data, right? So we got all the information in here. So this is the model that counts for moisture and suction effects, and actually it's very interesting to know that how many years, I think probably payment engineering was the first engineering that we had in the world, probably this one on water. We've been designing roads and building roads forever, right? Hundreds of years. And only until 2000 that we start incorporating the suction effects into the payment design analysis. So I'm talking to you that this is also This is just right now, right? We did it before that was, very empirical factors here and there. Okay. So here are the steps that I want you to follow. And this again is a prediction without using final element modeling, without using the questions, all of these things. You're obviously going to need the climate, right? Because you're going to know what is the climate of the region. And again, I'm going to go pretty on top of it, and you're going to ask questions if you have. And you're going to have the groundwater table, and I'm going to tell you the groundwater table is a great depth, okay, at this point. This is soil that are subjected to. And basically, with this climate, we estimate the third wind moisture index. The third wind moisture index, I'm gonna go for that in a second, is a humidity or aridity index that represent the climatic conditions of a site. Okay? So instead of putting a boundary condition when you have infiltration, evaporation, when you're doing CW or Plaxis or any other program, we're gonna put a factor that represents the condition on that, right? And this one with soil properties, and that's your question here. I'm gonna show you the model that we have, joining those together. We're gonna get the suction at equilibrium of a particular site, okay? What I'm telling you is you're gonna have exactly the same soil here and in the desert in the Sahara. And the suction at equilibrium of the two soils will be different, right? Because of the environmental conditions that you have, all right? So the soil can be exactly the same pore size, the same, pore network, the same capillary, but if you have a different environmental condition, the suction at equilibrium is gonna be in the graph in another place, right? In another place. Because it's gonna try to get more water, because it's gonna be always evaporation trying to get in here, or more infiltration, so it's gonna have more water, and the suction will be different, all right? It's very easy. You got the saltwater characteristic curve, you understand that. With the matrix suction that you got at equilibrium condition, if you have always this, infiltration evaporation forever, or a long-term condition, you got this equilibrium condition for that site, okay? And if you have the saltwater characteristic curve, you can imply the moisture content. Now, to me, that will be enough to have this guy. Didn't go away, this guy. But pavement engineering do not use suction, okay? They use a surrogate, and they use the moisture contents, all right? Because this is easy for them to understand. He understands suction. This is easy for them to measure in the lab, and it's easy for them to, and this is being the norm, They don't want to talk about suction, okay? Fine, we got the saltwater characteristic curve, we gave them moisture content or degree of saturation, okay? With together, another question that we have today here from Ahmad, we use also freeze-thawing adjustments, and unfortunately that's why I went for your answer, because I didn't have this in here. We use those two, and we calculate environmental factors. You're going to be calculating only the environmental factors for the frozen condition, right? But again, if we have freezing and thawing conditions, we need to make adjustments to this value. We're not going to go to that. Calculate environmental factor, okay, that now can be multiplied, right? Can be multiplied by the environment, by the optimum moisture content on that. And I'm going to be using a long-term condition, right? I'm going to give you one TMI that represents the value at equilibrium for that site. But I can give you also TMIs for every month to represent summers, to represent winters, right? So environmental factors actually can be varying with time if I give you factors every month. But this one that I'm giving you is kind of an annual condition, and it's going to be like that forever. Or, it's that site, that's the condition you get. And then actually you multiply this one by the optimum resilient modulus that you know how to get, and get the resilient modulus at equilibrium conditions. So the third wind moisture index, this is the guy that represents, this is actually the equation that we got for here. It seems to be simple, And it's not that simple. But again, it represents an annual index. This is precipitation and potential evaporation. Again, you got, it's a function of many parameters. I'm going to have you reading this thing. Okay? But just to give you, it's a balance between the rainfall and the evaporation we have. All right? It's a balance of that. There are equations to calculate the potential the actual evapotranspiration. This is the difficult thing to get, all right? And there are equations available for that I'm not going to ask you to solve because it's going to take you 3 days to do the spreadsheet and solve it. So I'm going to give you the TMI already, okay? But the data is going to be available in here. These are the equations that we use. We need heat index, and again, you take 12 months for something like that. You can take 12 months in 1996 or 2025 or anything, or you can take from June to June in 2020 and 21, okay? So the TMI actually can be calculated monthly if you want to. And here are the questions. It depends on, there was a question yesterday. There is a daylight correction based on the latitude you have. So you need to be very careful, because if you're using the design guide from the United States, this is for the northern hemisphere, okay? If you're going to be using that in the southern hemisphere, you need to use, a table to do it by hand. And these are the tables for the northern hemisphere, and we have one for the south. But, the factors are, some of them might be a little bit higher, but some of the factors are not that high. But basically, you just get the negative of the northern hemisphere here. These are some examples of the TMI, and I show you them this morning. Some of the Phoenix is minus 55, more evaporation than precipitation. Los Angeles is minus 32. So if you have negative, means that the balance is that during the year there is more evaporation than precipitation. Dallas is minus 2, so it's kind of in the balance, in the middle. This is Dallas, Texas. Miami plus 17, depends on the station you got. Orlando has, a little bit different number. Athens, Georgia, 33 plus 33. So positive means a lot of water in there. Negative means arid and semi-arid regions. Here are some data here for India that I found. These are the index for different climatic conditions that you have in here, or at least I found in here. And correct me if I am wrong. Probably you have a better considerations of that. I'm very sure you do. But I'm going to give you an idea what kind of TMIs we manage in India. All right? And for example, the Rajasthan area that we had in here is about minus 60. And the one that we got in Jaipur, which is around here, is about minus 30. Is that around here? Okay. And Guwahati is about plus 80 in there. So here we got in a very, very wet region, right? So you got those values in there, and we're going to be using those values to go forward. We're not going to calculate them, but the equations are there for you to use later on, and calculate the one for your region or for the soil that you need. Okay, so you got the TMI. Now you need to predict the equilibrium suction under the pavements, right? For that, so you got this one, and you're going to need some properties of the soil of the project. Remember, the thing with the roads, if the road is a longitudinal thing, you're going to need a lot of soil properties, because you're going to need probably miles and miles or kilometers of roads. It's not like a building. So you're going to be analyzing sections of your pavement during that. Soil properties, you get the matrix suction. So how do you get between TMI and matrix suction? I was telling you, you may have the same sand here or in Rajasthan, and you're going to have different suctions at equilibrium, right? Because evaporation or precipitation. And we visited about 30 sites within the United States with my good friend Yasan Ayaki, or also Uganda Pereira. He's from Sri Lanka. And we worked together on this back in 2008. And we went and actually we cored through the roads. like the same that we did for LTPP. Well, they did for LTPP, we did in here. Very carefully coring, not to get water in there. You know that those coring machine gets hot if you don't put water, right? You have to put water in there. Well, we couldn't put water in there. So we have to chisel at the end to get the core out and just, dig for the soil. And it was very nice work, but a lot of work. Spent about a year in the road doing that, all right? Collecting data from this road. And we measured what properties they have. We got Atterberg limits, water contents, the density of the soil, grain size distributions, and we measured the suction that we got. We did it close to cracks of the pavement and away from the cracks because we wanted to be the one at equilibrium, one that we had no water in there, right? To figure that out. And based on that, we got all this data and we created family of curves in which we were able to relate the Thorwen moisture index. This one was all the way to United States, and I mean, we got all the TMIs available in there, right? And we were able to put all these points in there and calculate the suction value for granular material and for subgrade materials. And that's how we create this family of curves. That was his thesis, Pereira's thesis, and that's how we relate the soil properties to the TMI and the suction of the soil. So it's a little bit different because of the suction. But it's not the soil type, it's the environmental that will change the property, the soil. And we just did very nice work in there. Okay, this one is the model for granular-based materials. And that's or for sand materials, sands with no PI pretty much, or very low PI. And this is the soil for the subgrade material, okay, higher PI. And they were a function of passing 200 at WPI. So you're going to have in there models to go from TMI to suction. Now you got suction, now you need saltwater characteristic curves, right? You can go to the laboratory and measure them, or you can use, you need the saltwater characteristic curve, right? So you can use this is the saltwater characteristic curve. Those are many, many models. If you do data points in your laboratory, you have many, many models to do the regression analysis from Brooks and Corey all the way to the Friedland equation that are a little bit more complicated. These are the testing that, I'm not going to go through that. We already went through that in this one. And I have in here a family of curves for you. Okay. How do you get that one? Well, we use about 1,227,000 soils to do that. How do you get this data? Okay. Well, I went to the National Resources Conservation Service from the U.S. Department of Agriculture. If you figure out the agricultural engineers and the agronomists and all of these have been using suction for 100 years. And that's what we get. Actually, that's what everybody got, the condition of that, right? So basically, we do have, we put together a national catalog of saltwater characteristic curve because that database was created with the then Bureau of Public Roads, and therefore they got all these engineering properties for us in there. That is available online, so you can get. So we went over there, we got the soils. That was a thesis from Torres Hernandez, a great student also of mine, and basically he put together family of the same kind of soils depending on the geology that we had in there and on that. So with that, we basically made a catalog with about 32,000 plastic soils and about 4,500 non-plastic soils. And we create family of curves. That one actually was my thesis, the first family of curves that was available. And then he modified those with a mine was with about 300 soils that I got from the Murray Friedland. And this one was, 36,000 soils. So this is a great family. And then you got the saltwater characteristic curve for different, this is the plastic soil material, this is the granular based materials as a function of the D10 of the soil, okay? So you're gonna need what? Grain size distribution in here, you're gonna need passing 200 and PI to get that. So you can use those ones instead of reading. Or just if you have laboratory data, then you use that, right? You use that. And then we got now the suction, and now we can, the moisture content, and now we can relate it to the environmental factor, right? And that's the model that I show you in the morning. This is the model that is being used by the design guide. It has only two categories, one for fine-grained materials and another one for coarse-grained materials. And the other one is the model that was put together by Kerry in 2010, one of my great also PhD students. And basically you can see how the environmental factor changes for clay materials, for granular materials below, dry of optimum or wet of optimum, all right? So you got this model in there. There are equations, but you can use the graph as well, just to get that, the approximated value. I just put a big picture so you can just enter that easily, right? All right, so you get the stiffness of the material by calculating this one, modified by resilient modulus. And the typical resilient modulus from the laboratory at optimum condition are given in these tables, right? So I gave you a couple of soils, and you can just have the resilient modulus that we got in the lab that also you learn how to get it, right? And those are pretty much ranges of material that you can use. So the activity is you need to estimate the resilient modulus at equilibrium with these, steps that I've just put together for you. And basically, this is the resilient modulus that the subgrade or the soil will tend to reach during the life of the pavement structure. Use properties for soils D and F. D and F are here. I just took some soils from I think Holtz and Kovac's book or something. All right, so you got that. And this is the grain size distribution for those soils, soils D and F right here. One is a very sandy material, PI 0. This is the clay material. These are the liquid limit, plastic limit. D is a non-plastic. F is a plastic material. All right. These are the natural moisture content at the Atterberg limits. And here, I gave you saltwater characteristic curves, so you don't have to use my curves, right? So you can use those guys. Those are measured data for this thing. And there is all D and volumetric water content versus suction, and D and F. But now if I give this one, I put you to do the whole regression analysis, right? How much, Dr. Bharat, how much effort they need to put on the final exam? Little effort or a lot of effort? All right, let's. Yeah. Yeah, because this one might very well be a final exam. Yeah, they need to do that. Okay, right. So no, the examiner. So we're going to do something, because it's going to be a tutorial. It's going to be doing that. You're not going to use the saltwater characteristic curve data. You're going to be using the PI information you got and the passing 200 you got, and you're going to estimate based on the correlation of the equation, right? Why? Because if you don't do that, you're going to have to do the solver to do a regression analysis, right? And I don't want you to do that. It's a lot of work. Well, for a tutorial. All right. So you report the suction at equilibrium. You report the degree of saturation, resilient modulus at optimum, and the resilient modulus at equilibrium, right? It's pretty simple. Are 4 equations that you need to follow. Okay, so we're going to have in here the data, and we're going to have the first 2 rows in here. So 6 people in here doing soil D and Guwahati. All right? The last 2 rows and the last row that you have over there, we're going to be doing soil D in Jaipur. That's terrible. Okay, so then we got 1, 2, 3, 4 rows. The last, rows, we got 1, 2, 3, 4, 7 people there. We're gonna do the soil F in Guwahati, and the first 2 rows in here, you guys gonna do soil F in Jaipur. All right? So everybody okay with that? And I'm gonna be here. I don't know if you guys wanna do this right now, or you guys wanna do this during the evening, rest, and come here and report in that. Probably we're gonna do that. Yeah. So what time it is? 4:50. We're gonna come back tomorrow, and basically I want you to just do the table, right? Fill it up, whatever you got, okay, in the table, and it's gonna be so fun to see what the numbers are gonna be. Okay, can I work together with it? Yeah, you can work together. It's fine, okay? It's fine. I just want you to learn and go to the system and see.
Guys from the same city, right?
Huh?
Guys from the same city?
No. Whatever that, yeah. Are you guys the same city? Oh, here we go.
Same city, like Guwahati, Jaipur.
Yeah, exactly. Yeah. And the soil, like the one I divided, yeah. You can work together on that. Now, another thing is we can report that tomorrow in here and see what you get, okay? And if you have any question, I want you to make assumptions, okay? If I said, okay, there is some missing information in here or something like, go ahead and make an assumption. I said, I assume this. See what you get. I don't think you have many things to assume in there, but if you need anything, just be resourceful, okay? All right, guys, you guys, any questions? Do you got this material with you?
Yes.
You do? Okay, the last tutorial on that? All right, so you got the material, you got everything? Okay. Yes?
We did not discuss the coupled effect of traffic on resident models.
The effect of traffic. Yes, we did. We did, but I'm going. Okay, so where is the effect of traffic on the resilient modulus? And the resilient modulus at optimum, right? When you do the resilient modulus at optimum, what we look at this morning was that you have a stress sequencing, right? And you do a dynamic loading that is Haber sign, okay? That resilient modulus that you get in the lab is actually what represents the response of your material due to the traffic. So,
like we are doing the test at different sequence, different confining pressures and stress that is up. So at what confining pressure should I take the resistance?
well, at the stress condition that you're going to have in the field.
Based
Okay.
on the pavement thickness and
Exactly. So you're going to have a pavement thickness. You're going to have, well, I didn't go there. This is pavement design. That is not my forte. But basically, what you do is you take all these stress conditions that you have, and they're going to be low, medium, or high volume roads, on this one. And you're going to know what are going to be the deviator stress and the confining stress that you're going to need for that.
at a given depth,
Exactly.
at the top of subgrade layers.
On the top of the subgrade layer, exactly. And that's how you choose, based on that family of the resilient modulus that you get, which one is the one that you're going to be using for your conditions. That's exactly right. Okay. So, yes, you're going to need the number of repetitions that you're going to have in the road, and you're going to need figure out how, with that number of repetitions, what is the resilient modulus? Not that. I think it's with the stress state condition that you have. I don't have that information for you, yeah. But that's how you get that one. You get the stress conditions in the field, and then you use them to calculate what is the resilient module you're going to find for that. Okay.
So as an input, I think we have to give a trial modulus for each of the layer, or the design modulus.
Yes. So this resilient modulus at optimum is done for the granular base material, for the subgrade material, and for the subbase and subgrade material. So you get that one. And all of them are going to have the stress conditions that are in the field. I'm just trying to figure out how to relate this one to the number of repetitions.
Online people don't know.
Oh, what happened?
Question.
Oh, question.
Their assignment. Okay.
Oh, do we have any other parameters similar to TMI for freeze-thaw cycles? Yes, we do. The thing is, I didn't bring that in here. Okay, so here is what we do, Emad, but unfortunately, I didn't bring it in here. But let's see if I can do that. What in reality, these are the, oops. We got the granular, the asphalt pavement, AC, the granular material, granular base. And let's say you got no sub-base, but you have the subgrade in here, right? So you have those soils in here. And basically, we are calculating the TMI every month. Every month. So, and for every, we divided actually the subgrade into, you can divide it into different sublayers, right? Depending on the accuracy that you want to put all the parameters in here. So let's say you do have those, AC obviously, there is no flow through here. But then you said, okay, for time equals the first month, month number 1, we calculate that environmental factor, okay? And that's going to be an environmental factor in here for unfrozen condition. And in here, we're going to have an environmental factor for unfrozen, here too. And actually, depending on the number of sublayers that you have, this is unfrozen. So you're going to be using unfrozen environmental factor of them. You do the same for month 2, 3, 4. Let's say on month number 5, you start getting frozen depth conditions, okay? You calculate the frozen environmental factor in here, the frozen environmental factor in here is unfrozen, unfrozen, and so forth. The next one, it's 6 months, and so forth. And you're going to see the front of here going up and down because you calculate the frozen, and some of them are going to start into the thawing condition, and so forth. So you do have that in here. And basically what you find out is for the whole layer, because you're going to need to put this one into your resilient permanent deformation model, rotting models, you're going to have a composite value of what you get in order to figure out what is the condition. Now, the composite value will be with the depth, but with the time, you can have different values, right? So you got, again, the unfrozen environmental condition, the freezing condition, the thawing condition, and the comeback. And I have those, I didn't bring them in here, I just want the unfrozen, but I'm going to dig into my notes on this one, and I'm going to send you those equations, okay? And the equations are nothing but an empirical modulus or environmental factor when you do have frozen conditions, and an empirical reduction to a point, and an empirical equation in here to recovering depending on the soil type, okay? That's nothing more than that. But this one creates the environmental factors are different frozen and unfrozen conditions, okay? So yes, they are available, and I'm going to send them to you, Emad, okay? I'm just not going to use them to this activity. Do you guys understand that? Okay. All right, guys, so class is dismissed. I hope you guys can just spend, a few minutes doing that. 30 minutes or something like that, okay? And I want to see results tomorrow.
The online participants have not been given the assignment.
The what again?
The online participants.
So they didn't get the assignment.
Oh, they didn't get the assignment. So,
They should be under some town, Guwahati, Jaipur, something like. Under ABC, the class.
oh, no, oh, I see. Okay, how many we got in here? We got 4?
As of now, 4.
All right. Okay, so, Emad. What is it? I see what I mean. Yeah, okay. What we get? So, Emad, you're going to have soil D for Guwahati. Rohit, you're going to have soil D for Jaipur. Vavitra, you're going to have soil F for Guwahati, and it's Srinivasan, you're going to have Jaipur, soil F, okay? Okay. Emad, you're going to have soil D, which is the granular material. Okay, Emad, Guwahati, soil D. Thank you so much. Rohit, we got D, Jaipur. Bhavitra, soil F, Guwahati, and Srinivasan, soil F, Jaipur. All right. All right, guys. Hope you have a wonderful evening, and the class is dismissed. You may go. Thank you so much. That was good. Srinivasan. Okay. Jaipur. Thank you. Did I? Okay. I thought I had disconnect them. This is difficult.